For centuries, humanity has looked to the stars and made assumptions about the universe. From the Earth-centered models of ancient astronomy to the heliocentric system proposed by Copernicus, our understanding of space has evolved through major revolutions in thought. Yet, even with the incredible advancements of modern science, there are many ideas about space that remain deeply ingrained in our collective consciousness. We assume that these ideas are absolute truths, unquestionable pillars upon which our understanding of the universe rests. But what if everything we know about space is wrong? What if the fundamental principles that have shaped our understanding of the cosmos are flawed, incomplete, or based on outdated assumptions? In this chapter, we're going to explore the conventional wisdom that governs our view of space and ask the uncomfortable question: are these long-held beliefs actually holding us back from seeing the universe as it truly is? Humanity's relationship with space has always been defined by our attempts to understand it, to explain its workings, and to define our place within it. We've built upon the ideas of the past, continuously refining and expanding them. However, as we delve deeper into the cosmos, we've encountered more anomalies, contradictions, and questions that don't neatly fit into our established models. These inconsistencies suggest that there might be more to space and reality than we can currently comprehend. Some of the greatest minds in science and philosophy have started to challenge the conventional wisdom, proposing new theories and models that radically alter our perception of the universe. In this chapter, we will begin by questioning the fundamental ideas that most of us accept as truths. From the Big Bang Theory to our understanding of gravity and the speed of light, we'll examine why these concepts, which have shaped scientific discourse for decades, may not be as invulnerable as we once thought. What if these ideas, these pillars of modern science, are simply placeholders for a greater truth that we haven't yet discovered? What if everything we know about space is just the beginning of a much larger and more complex story? The Big Bang Theory. The beginning of everything? One of the most widely accepted ideas about space is the Big Bang Theory, the notion that the universe began as an infinitely small, hot, and dense point around 13.8 billion years ago. This theory is central to our understanding of the cosmos. Everything from the formation of galaxies to the cosmic microwave background radiation, CMB, is interpreted through the lens of the Big Bang. It offers a clear, linear explanation for the origins of the universe, a sudden expansion from a singularity that continues to this day. However, despite its widespread acceptance, the Big Bang Theory has numerous unanswered questions and apparent contradictions. For one, the theory does not adequately explain what caused the Big Bang itself. What happened before the event, and what conditions could have led to such a singularity? According to the laws of physics, a singularity is a point where space and time lose all meaning. So how could it have birthed the vast and structured universe we see today? Additionally, the expansion rate of the universe is another conundrum. Observations suggest that galaxies are moving away from us at increasing speeds, a phenomenon attributed to dark energy. However, the way dark energy is tied into the Big Bang Theory remains unclear. If the Big Bang was the origin of all matter and energy in the universe, how do we account for the mysterious force that seems to be accelerating the expansion of the universe? The current models don't fully explain this. The fact that the Big Bang Theory leaves so many gaps and questions open to interpretation is one of the first signs that our understanding of space might be incomplete. Could there be a more accurate or comprehensive model for the origin and structure of the universe? One that doesn't rely on a singularity or a sudden explosive event? The heliocentric model, our place in the universe. For much of human history, the prevailing belief was that the Earth was at the center of the universe. This geocentric view of the cosmos was deeply ingrained in many ancient cultures and was supported by religious and philosophical beliefs. It wasn't until the Copernican revolution in the 16th century that the heliocentric model, that the Earth orbits the Sun, began to take hold. This idea, popularized by Copernicus and later refined by Kepler and Galileo, revolutionized our understanding of space, making the Sun, not Earth, the center of the solar system. Even with the heliocentric model, however, our view of the universe was still limited. We thought of ourselves as the center of the universe, with Earth at the heart of all creation. In the 20th century, the discovery that the Milky Way galaxy was just one of billions in the universe completely shattered this idea. In fact, the Earth is not even located in the center of our own galaxy, but rather on one of its spiral arms in a relatively quiet region of space. The realization that the Earth was not at the center of everything was a profound shift in human perception. Yet, this shift didn't end our search for meaning in space. We still want to know where we fit into the larger cosmic puzzle. Are we alone in the universe, or is Earth just one of countless planets in a vast cosmic ocean? The more we learn about space, the more it seems that humanity is just a small speck in an unfathomably vast and complex universe. Yet, we continue to cling to the idea that we are at the center of something, whether it's our solar system, our galaxy, or our understanding of reality itself. The belief that we are the focal point of existence is deeply ingrained in human nature, but as we continue to explore space and learn more about the scale and complexity of the universe, we may need to abandon this perspective entirely. Could we be wrong to place so much significance on Earth? Is there a more humbling and expansive view of the cosmos that we need to adopt? The speed of light. A universal constant or a limitation? One of the fundamental principles of modern physics is the speed of light. According to Einstein's theory of relativity, nothing can travel faster than the speed of light, which is approximately 300,000 kilometers per second. This principle has been a cornerstone of modern physics for over a century, and it governs everything from the structure of space-time to our understanding of gravity and energy. However, recent developments in quantum mechanics and the study of quantum entanglement have challenged our understanding of the speed of light. Quantum entanglement, often described as spooky action at a distance, is a phenomenon where two particles become linked, and changes to one particle can instantly affect the other, no matter how far apart they are. This appears to happen faster than the speed of light, suggesting that instantaneous communication or faster-than-light travel might be possible after all. While these phenomena don't necessarily contradict relativity, they do suggest that our understanding of space and time might not be as absolute as we thought. Could the speed of light, once considered the ultimate limit, be just a limitation of our current understanding rather than a fundamental truth of the universe? Are we on the cusp of discovering new principles of physics that could allow for faster-than-light travel or communication? These questions challenge our most basic assumptions about space and time and could lead to a new era of exploration. The nature of gravity. The force. We don't fully understand gravity is perhaps the most familiar force in our daily lives. It holds us to the Earth, governs the orbits of planets, and shapes the structure of galaxies. However, despite its central importance in the universe, gravity remains one of the most poorly understood forces in physics. While Newton's law of gravity and Einstein's theory of general relativity provide excellent models for how gravity works on large scales, we still don't know why gravity behaves the way it does. For example, general relativity describes gravity as the curvature of space-time caused by massive objects. Yet, when it comes to the quantum scale, where particles behave unpredictably, gravity doesn't fit neatly into our current understanding of the universe. There are contradictions between how gravity works on large scales, where general relativity applies, and how it operates on the smallest scales, where quantum mechanics prevails. This divide between the quantum and macroscopic worlds remains one of the greatest challenges in modern physics. Could the rarest phenomenon discovered in the universe provide new insights into how gravity operates? If gravity is not as fixed or absolute as we believe, what does that mean for our understanding of space-time and the forces that shape the cosmos? The answers to these questions could rewrite much of what we know about gravity and force us to develop new models of space and time. The shocking truth: rethinking space. As we reflect on the conventional wisdom about space, ideas that have shaped our understanding of the cosmos for centuries, It's clear that much of what we take as truth may be far from complete. From the Big Bang to the speed of light, from dark matter to gravity, the discoveries we make today may challenge the assumptions that have defined our reality for so long. This raises the question, what if we are wrong about everything? The truth is, we don't yet know the full extent of the universe's mysteries. While we have made incredible strides in our understanding, we are only scratching the surface. The discovery of new phenomena and the development of new technologies will continue to challenge our assumptions, leading to new questions and new answers. The shocking truth may be that everything we know about space is just the beginning. The universe is far stranger, far more complex, and far more mysterious than we could have ever imagined. The more we discover, the more we realize that our current models may be incomplete and that the real nature of the universe is something far more profound and awe-inspiring than we can even conceive. Conclusion. Embracing the unknown. In the end, the real beauty of space exploration lies not in finding all the answers, but in the questions themselves. The rarest phenomena, the unexplained mysteries, and the discoveries that force us to rethink everything we know are what make the universe so captivating. Embracing the unknown and pushing the boundaries of what we understand is the essence of scientific inquiry and human curiosity. As we continue to explore the universe, we must remain open to the possibility that everything we know might be wrong, and that the true nature of space and time is far more extraordinary than we ever imagined. The journey of discovery is just beginning, and it's a journey that will reshape our understanding of the cosmos and ultimately our place within it. The Big Bang Theory has been the dominant model for understanding the origins of the universe for nearly a century. According to this theory, the universe began as a singularity, an infinitely small, hot, and dense point, roughly 13.8 billion years ago. From this initial moment of explosive expansion, the universe as we know it began to unfold, giving rise to galaxies, stars, and planets. This idea has shaped much of modern cosmology, offering an elegant explanation for the observable phenomena we see in space, from the cosmic microwave background radiation to the expansion of galaxies. However, as we delve deeper into the mysteries of the universe, we begin to see cracks in this long-standing theory. The Big Bang may not be the ultimate explanation for the beginning of the universe, and the more we learn, the more questions arise. Could the Big Bang not be the true origin of everything? What if this theory, so central to our understanding of space, is fundamentally flawed? What if there's something more to the story, something that we've overlooked for so long? In this chapter, we will explore the problems with the Big Bang theory, examine alternative models that challenge the idea of a singular beginning, and discuss the new frontiers in cosmology that could change our understanding of the universe's origin. The Big Bang. A flawed starting point? The Big Bang theory, in its simplest form, posits that the universe began from a singular point, a singularity. At this point, the universe was infinitely dense and hot, a condition so extreme that our current understanding of physics cannot fully explain it. The theory then suggests that the universe began expanding rapidly in a process known as cosmic inflation, spreading matter and energy throughout space and giving rise to the vast universe we see today. While the Big Bang theory has been immensely successful in explaining many aspects of the universe, such as the cosmic microwave background radiation and the observed redshift of galaxies, it still leaves many unanswered questions. Most notably, it provides no explanation for what caused the singularity to exist in the first place. What set the universe into motion? What came before the Big Bang? And more importantly, is the Big Bang truly the beginning of everything? One of the major issues with the Big Bang theory is that it doesn't explain the singularity itself. The concept of a singularity is inherently problematic, as it suggests a point in space-time where the laws of physics break down. At this point, density and temperature are infinite, and the known laws of physics fail to hold. In other words, the very idea of a singularity is outside the bounds of our current scientific understanding. So, if the universe began from this singularity, How can we claim to truly understand its origins? Additionally, the Big Bang Theory operates under the assumption that time and space as we know them began at the moment of the Big Bang. However, this idea of a singular beginning might be an oversimplification. Time and space, as understood by Einstein's theory of general relativity, are tied together in a fabric known as space-time. The notion that time itself had a starting point is a philosophical and scientific dilemma that challenges our understanding of reality. Could time exist before the Big Bang? And if so, what did that imply about the origin of the universe? The limits of the Big Bang Theory. The Big Bang Theory has brought about immense progress in our understanding of the cosmos, but it also has limitations. These limitations become evident when we examine certain phenomena that the theory struggles to explain. For instance, the cosmic microwave, background radiation, is one of the most significant pieces of evidence for the Big Bang. It is a faint afterglow of the initial explosion that has been detected across the universe. While this radiation supports the idea of a hot, dense early universe, it also poses questions that the Big Bang Theory cannot fully answer. Specifically, why is the microwave background radiation so uniform across the universe? Shouldn't the universe have cooled unevenly, with hotter and colder regions? Another challenge for the Big Bang Theory is the flatness problem, the observation that the universe appears to be geometrically flat, meaning that the angles of triangles add up to 180 degrees and the curvature of space is nearly zero. According to the Big Bang model, the universe should have started out with a certain amount of curvature, but observations show that the universe is remarkably flat. The theory doesn't explain why the universe is so close to being flat and why the universe's geometry should have evolved in such a precise way. Lastly, the Big Bang Theory does not address the origin of matter. While it explains the evolution of the universe after the Big Bang, it doesn't account for where all the matter came from in the first place. The theory suggests that the universe began as an incredibly hot, dense state, but it doesn't explain how that state came to be. What created the initial conditions for the Big Bang, and where did the fundamental particles come from? Alternative models to the Big Bang. Given the limitations of the Big Bang Theory, many alternative models have been proposed to explain the origin and structure of the universe. Some of these models challenge the notion of a singular, one-time event like the Big Bang, suggesting instead that the universe may have existed in a different form before the event we call the Big Bang. These alternatives seek to address the problems posed by the Big Bang Theory and offer new perspectives on the origin of the universe. 1. The cyclic universe theory. One alternative to the Big Bang Theory is the cyclic universe theory, which posits that the universe undergoes an endless series of expansions and contractions, each cycle representing a Big Bang followed by a Big Crunch. In this model, the universe does not have a singular beginning, but has existed in a series of cycles, with each one starting with a Big Bang and ending with a collapse, only to be followed by another expansion. The cyclic model addresses some of the issues with the Big Bang Theory, such as the flatness problem and the question of what came before the Big Bang. According to this theory, the universe has always existed in some form, and time itself is cyclical rather than linear. This model also provides a potential explanation for the observed uniformity of the cosmic microwave background radiation, as each cycle could reset the conditions of the universe. However, while the cyclic theory offers an elegant alternative to the Big Bang, it is still speculative. There is currently no direct evidence supporting this model, and questions remain about how the universe could undergo such dramatic expansions and contractions without fundamentally altering the laws of physics each time. 2. The steady-state theory. The steady-state theory is another alternative that challenges the Big Bang model. Proposed by Sir Fred Hoyle, this theory suggests that the universe has no beginning or end, but is in a constant state of expansion. According to the steady-state theory, as the universe expands, new matter is continuously created to fill the gaps, maintaining a constant density throughout space. While the steady-state theory was popular in the mid-20th century, it fell out of favor when evidence for the Big Bang became overwhelming. However, it still raises interesting questions about the nature of the universe's evolution. If the universe is truly in a steady state, then perhaps there is no singular event that marks the beginning of everything. Space and time could be eternal and unchanging. 3. The multiverse. Theory. The multiverse theory proposes that our universe is just one of many in a vast multiverse, a collection of infinite or nearly infinite universes, each with its own laws of physics and initial conditions. According to this theory, the Big Bang could represent the beginning of one particular universe, but it would not be the origin of everything. Instead, our universe is just one bubble in a much larger cosmic structure, with other universes existing alongside ours in a vast, unobservable multiverse. The multiverse theory offers a way to explain some of the fine-tuning of the universe, such as the specific physical constants that make life possible. In a multiverse, different universes could have different properties, and we just happen to live in one that is hospitable to life. This theory also provides a possible explanation for the fine-tuning problem, which questions why the universe appears to be perfectly suited for life. While the multiverse theory is fascinating, it is highly speculative, and there is currently no empirical evidence for the existence of other universes. However, it raises important questions about the nature of reality and the limits of our understanding. The implications of reconsidering the Big Bang theory. The possibility that everything we know about the Big Bang could be wrong has profound implications for science. If the Big Bang is not the true origin of the universe, then we may need to rethink our entire understanding of cosmology. This could lead to new insights into the nature of space-time, gravity, and dark matter, as well as a deeper understanding of the universe's ultimate fate. Reconsidering the Big Bang theory could also have philosophical implications. If the universe doesn't have a singular beginning, does it mean that time itself is infinite? Does this change our understanding of causality and the nature of existence? These are questions that will challenge scientists, philosophers, and theologians for years to come. Furthermore, if the Big Bang theory is incorrect, it could pave the way for new technologies and scientific breakthroughs. For instance, understanding the true origins of the universe could lead to advancements in quantum mechanics, gravitational physics, and even space travel. By opening up new avenues of inquiry, we could gain insights into the deepest mysteries of the cosmos. Conclusion. The end of the Big Bang. The Big Bang theory has served as the foundation of modern cosmology for decades, but as we explore the mysteries of the universe, we are beginning to see its limitations. From the origin of the singularity to the questions about time and space itself, the Big Bang theory may not be the final word on the universe's beginning. Instead, it may be one step in a much larger and more complex story. The possibility that everything we know about the Big Bang is wrong forces us to rethink our place in the cosmos and the fundamental principles that govern the universe. The answers to these questions will shape the future of cosmology and could reveal a new and more accurate picture of the universe's origin. As we continue to explore these possibilities, we may find that the true nature of the universe is far stranger, more complex, and more wondrous than we could ever have imagined. The discovery of dark matter and dark energy is one of the most significant achievements of modern cosmology. These two mysterious forces are believed to make up about 95% of the total mass energy content of the universe. Yet, despite their overwhelming influence on the structure and expansion of the cosmos, we have virtually no understanding of what they truly are. In fact, they are not directly observable. We can't see them, touch them, or measure them in any traditional sense. Instead, we infer their existence based on their gravitational effects and the way they influence the motion of galaxies and galaxy clusters. It is ironic, then, that we have come to accept dark matter and dark energy as truths, forces that shape the universe, yet remain entirely invisible. The truth is, even the most advanced scientific models cannot fully explain these forces. But they are accepted as fact because the evidence supporting their existence is undeniable. However, what if everything we think we know about dark matter and dark energy is wrong? What if these forces, which we have built much of our understanding of the universe around, are not what we think they are? In this chapter, we will explore the enigmatic nature of dark matter and dark energy, why we've accepted them as truths, and why our understanding of them might be flawed. We'll also examine new theories that challenge the accepted models and question whether these forces might be entirely different from what we have assumed. Are we missing something fundamental in our understanding of these cosmic forces, or are we simply too attached to our current models to recognize a deeper truth? The mysterious nature of dark matter. Dark matter is one of the most intriguing and elusive components of the universe. We know that it exists because we can observe its gravitational effects on visible matter. For instance, the way galaxies rotate faster at their edges than they should based on the amount of visible matter present suggests that something invisible, yet massive, is exerting a gravitational pull. This something is dark matter. Despite extensive efforts, we have never directly detected dark matter. It does not interact with light, electromagnetism, or any of the forces we are familiar with except gravity. This means that, unlike ordinary matter, dark matter cannot be seen with telescopes, nor does it emit or reflect light in any detectable way. It remains entirely invisible, hiding in the background of the universe, and yet it accounts for approximately 27% of the total mass in the universe. For decades, scientists have speculated about the nature of dark matter. Many believe that it is made up of unknown particles, such as weakly interacting massive particles, WIMPs, or axions. These particles would have mass and interact gravitationally with normal matter, but they wouldn't interact with light or other electromagnetic radiation. Despite extensive experiments, no dark matter particles have been conclusively detected. The search for dark matter continues, and every new failed experiment leads us back to square one. However, we can still detect its effects on a cosmic scale, and its presence remains an integral part of our understanding of the universe. But is dark matter really made up of these unknown particles, or is there something we're missing in our current understanding of gravity? Could dark matter, rather than being a new form of matter, be a manifestation of a fundamental flaw in our understanding of gravitational forces on cosmic scales? The dark energy conundrum. If dark matter is mysterious, dark energy is even more so. While dark matter has mass and exerts gravitational pull, dark energy is thought to be responsible for the accelerated expansion of the universe. In fact, dark energy is believed to account for about 68% of the total energy content of the universe. The discovery of dark energy came in 1998 when two independent teams of astronomers found that the expansion of the universe was not slowing down, as expected, but actually accelerating. This unexpected result led to the hypothesis that some unknown force, dark energy, was driving the acceleration. The effects of dark energy are most apparent in the large-scale structure of the universe. In fact, dark energy is thought to be the driving force behind the cosmic expansion, pushing galaxies further apart and causing the universe to grow at an ever-accelerating rate. The fact that dark energy is so pervasive and powerful, yet still entirely undetectable, is one of the great mysteries of modern science. Unlike dark matter, which we can indirectly detect through its gravitational influence,
So that's how relativity connects to the quantum field.
Dark energy
It's
remains
beautiful.
purely theoretical. We cannot see it, measure it, or even understand its properties. And yet, it is believed to make up nearly 70% of the total energy in the universe. One of the most confounding aspects of dark energy is its negative pressure. This strange property seems to repel matter rather than attract it, causing the expansion of space itself to speed up.
Where light years
But
are
the
but a
nature
whisper.
of dark energy, what it actually is, how it operates, and why it behaves in this counterintuitive way, remains a mystery. Many scientists suspect that dark energy is not a new form of energy, but rather a manifestation of some underlying principle of physics that we have yet to discover. Could dark energy, rather than being a force that exists on its own, be an effect of something much deeper? Could it be related to
The
the vacuum
alignment
energy of
holds true.
space? Or is it a completely
Yes,
new form of energy
just
that
as the
behaves in
tablets
ways
foretold.
we cannot yet comprehend? These questions highlight the gaps in our understanding of the universe and suggest that we might be overlooking something fundamental about the nature of space and time itself. The problem with our current models of dark matter and dark energy. The more we learn about dark matter and dark energy, the more we realize that our current models are incomplete and perhaps even fundamentally flawed. While these forces are essential to our understanding of the universe's structure and expansion, we've reached the limits of what our current tools and theories can explain. For instance, the assumption that dark matter is composed of WIMPs or axions is still just that, an assumption. We have no direct evidence to support this theory, and experiments designed to detect these particles have failed time and time again. Could we be looking for the wrong type of particles? Or is there an entirely different explanation for the gravitational effects we observe in galaxies? Similarly, our understanding of dark energy is based on the assumption that it is a constant force, an energy that permeates all of space and causes the universe's expansion to accelerate. However, recent studies have raised doubts about this idea. Some scientists believe that dark energy might not be constant, but could change over time, or that it might even be the result of some unknown interaction between gravity and quantum fields. If this is true, our models of cosmic expansion and the fate of the universe would need to be entirely reworked. These gaps in our understanding suggest that there may be deeper, more fundamental principles of physics that we have yet to uncover.
Superposition achieved.
It's possible
the
that
energy
dark
readings
matter
are stable.
and dark energy are not entirely separate forces, but are interconnected in ways we don't yet understand. It's even possible that they are not forces at all, but are phenomena caused by the breakdown of known physics in certain conditions. New theories, challenging the conventional wisdom.
As we journey into the cosmic ocean, we find
As
ourselves
scientists
adrift
continue
in
to
a
probe
sea
the
of
mysteries of
stars
dark matter and
shadows.
dark energy, several new theories are emerging that challenge our current understanding. One promising theory is that dark matter may not be matter at all, but rather a manifestation of an entirely new form of gravitational interaction. This theory, known as modified gravity, suggests that the effects attributed to dark matter are actually the result of gravity behaving differently on large cosmic scales. According to this theory, our current understanding of gravity, based on Einstein's general relativity, may need to be extended or modified to explain the observed behavior of galaxies and galaxy clusters. Similarly, alternative theories of dark energy suggest that it may not be a mysterious constant force, but rather an effect of quantum fluctuations in space itself. These fluctuations could create a form of vacuum energy that drives the expansion of the universe. In this view, dark energy would not be a separate force, but rather a manifestation of the fundamental properties of space-time. If this theory holds true, it could lead to a radical shift in our understanding of both dark energy and the fabric of space itself. Another intriguing theory is that dark matter and dark energy are somehow related, perhaps being different manifestations of the same underlying phenomenon. If this were the case, it would revolutionize our understanding of the universe, potentially unifying the forces that govern both the structure of the cosmos and its expansion. By studying the rare phenomenon recently discovered, scientists may be able to unravel the connection between these elusive forces, offering a new model that accounts for both dark matter and dark energy in a single framework. The road. Ahead, new frontiers in research. The next step in understanding dark matter and dark energy lies in further exploration and experimentation. Advances in technology, such as more sensitive detectors, more powerful telescopes, and new methods of probing the universe, will enable scientists to study these forces in greater detail. The discovery of the rarest thing in the universe could also provide new clues about dark matter and dark energy, offering a fresh perspective on these long-standing mysteries. For instance, space-based observatories like the James Webb Space Telescope and the European Space Agency's Athena Observatory are expected to provide more detailed images of distant galaxies, helping scientists measure the effects of dark matter and dark energy with greater precision.
The heart of the
Additionally,
Dragon's Breath
new particle
nebula.
detectors could eventually allow for the direct detection of dark matter particles or new forms of energy that we've never observed before. The future of dark matter and dark energy research is full of exciting possibilities. As we continue to explore the universe and refine our theories, we may discover that what we once thought we knew about the cosmos is just the beginning of a much deeper, more profound story. Conclusion: the unseen forces of the universe. Dark matter and dark energy are two of the most puzzling and mysterious forces in the universe. While we have made significant progress in understanding their effects, we are still far from fully comprehending their true nature. As we continue to search for answers, we must remain open to the possibility that our current models are incomplete or even fundamentally wrong. The rare phenomenon recently discovered may be the key to unlocking the mysteries of these unseen forces and offering new insights into the structure and evolution of the universe. What we thought we knew about dark matter and dark energy could very well turn out to be just the beginning of a much larger, more complex story. One of the most enigmatic and awe-inspiring objects in the universe, black holes have long captured the imaginations of both scientists and the general public. For decades, they have been regarded as the ultimate cosmic mystery, regions of space where gravity is so intense that nothing, not even light, can escape. Black holes are often portrayed as the endpoints of collapsed stars, where matter becomes infinitely dense and space-time is warped beyond recognition. But are they really what we think they are? Despite their name and their reputation as mysterious, destructive forces, black holes may not be as simple or as sinister as we once believed. In this chapter, we will take a closer look at black holes and challenge the conventional wisdom surrounding them. Are black holes truly the cosmic voids we've made them out to be, or are we missing something fundamental about their nature and behavior? The traditional view: what we think we know. The concept of a black hole was first introduced in the 18th century by the English scientist John Michell, who proposed the idea of a dark star, a star so massive that its escape velocity,
was a
or the
canvas of
speed needed
endless
to escape
darkness,
its gravitational
waiting
pull,
for the
would
colors of
exceed the speed
creation
of
to
light.
bloom.
However, it wasn't until the 20th century, with Einstein's theory of general relativity, that the modern understanding of black holes began to take shape. According to general relativity, a black hole is a region of space where gravity is so strong that it warps space-time in a way that forms a singularity, a point of infinite density and curvature where the laws of physics as we know them cease to function. Surrounding the singularity is the event horizon, the point of no return beyond which nothing can escape, not even light. This traditional view of black holes as singularities with event horizons is grounded in the mathematical models of general relativity. These models predict that when a massive star runs out of fuel, it collapses under its own gravity, eventually forming a black hole. The singularity, with its infinite density, is considered the core of the black hole, while the event horizon marks the boundary beyond which all matter and radiation are trapped. In many ways, this view of black holes fits neatly into our understanding of the universe. They are the ultimate endpoints of massive stars, the most extreme objects in space. They are the final destination of matter and energy, and their gravitational pull is so strong that they govern the dynamics of entire galaxies. For decades, this theory has provided an elegant explanation for some of the most mysterious and powerful objects in the cosmos. The singularity problem.
Advanced technologies
What happens
like
at the
gravitational
center?
wave detectors and radio
One of
telescopes
the biggest issues
are
with the
transforming
traditional
our
view of
ability
black
to
holes
explore space.
is the concept of the singularity. In classical general relativity, the singularity is a point where the gravitational pull becomes infinitely
The
strong.
M-sigma relation
The
doesn't
density
hold
of
here.
matter
Look at the data.
reaches
It requires
infinity.
a localized field fluctuation.
At this point,
if we adjust for the dark
space-time
matter halo,
itself
the new
is thought
framework
to
is
break
stable.
down, and the known laws of physics cease
Cosmic
to apply.
voids formed as a
However,
result of the
this
universe's
presents a
expansion
fundamental
after the Big
problem.
Bang.
The idea of
Some
infinite
regions of
density and infinite curvature
Cosmic
is not just
voids vary in
mathematically
size,
challenging.
from
It's
tens of
physically
millions to
implausible.
hundreds of millions of light years
Infinity
across.
is a concept that has no real
Could
counterpart
this new
in the
anomaly
physical
be
world.
tied to dark matter?
It's a mathematical
the invisible
abstraction,
substance
not
that makes up
something that can be
most of the
physically
universe's
realized.
mass?
The existence of a
Could
singularity
this rare
challenges
discovery
the
be tied to
foundations of our
dark matter
understanding
or
of physics,
dark energy?
because it
Two of
suggests
the
that the
universe's
laws of nature
greatest
break
mysteries.
down completely under extreme conditions. To resolve this issue, many physicists believe that general relativity must be modified or replaced
Dark
by
matter
a more
plays a
complete
crucial
theory of
role in the
gravity,
universe's
one
structure,
that incorporates
helping to
quantum
form
mechanics,
galaxy
the
clusters
theory
and
that governs
filaments
the
that
behavior
surround
of particles
voids.
at the smallest scales. This brings us to one of the most pressing questions in modern physics. What happens inside a black hole? Quantum gravity,
Deep
the
within the
search
galactic
for a
core,
unified theory.
scientists have witnessed the impossible.
The discovery of a black hole,
stable-
The gravitational
singularity, presents a
distortion is off the
significant
charts.
challenge for
Cross-reference
physicists
the radio
because it
data.
involves
It's a
two
perfect
competing
match.
theories.
We did it.
General
We actually
relativity,
did it.
which describes the large-scale behavior of objects in space, and quantum mechanics, which describes the behavior of particles on the smallest scales. While both theories are highly successful in their respective domains, they are fundamentally incompatible when it comes to extreme environments like black
There's
holes.
nothing here.
General relativity
A void.
treats gravity as a smooth
massive.
curvature of space-time, while quantum mechanics treats forces, including
energy
gravity,
readings
as
are
quantized,
unprecedented.
meaning that they come in
Look at the
discrete units.
gravitational lensing. It
The
confirms
combination
the
of these two
propulsion
theories
theory.
into a single
That's right.
framework,
The
theory
existence of
quantum
these
gravity,
voids
is one of
challenges
the
our
biggest
understanding
goals
of
of modern
space and
theoretical
time.
physics.
They symbolize
But
not
until
just
we develop
emptiness.
such a theory, the true nature of black holes
The
will
Milky
remain
Way,
elusive.
with its hundreds
Quantum
of billions
gravity
of
would help us
stars, is a
understand what
vast
happens
and vast
inside a black
galaxy.
hole, especially at the singularity. Some physicists believe that quantum effects may prevent the formation of an actual singularity, replacing it with a quantum foam, where space-time becomes extremely chaotic and fluctuates at incredibly small scales. This quantum view of the black hole might eliminate the problem of infinite density and offer a more complete picture of what happens at the heart of these
The
enigmatic
search
objects.
for this rare phenomenon
However,
was not
quantum
easy.
gravity is
It
still a
required
speculative
years
field,
of technical
and there is currently
knowledge.
no consensus on what such a theory would look like. The discovery of a rare phenomenon, perhaps linked to quantum gravity or the behavior of black holes, could provide the experimental
This
evidence
discovery
needed to
could
guide us
rewrite
toward a
our
more complete
of the
understanding.
universe's
The
evolution.
event horizon, a gateway or a trap. The event horizon is the boundary surrounding a black hole, beyond which nothing, not even light, can escape. It is often depicted as a one-way gate, trapping anything that crosses it inside the black hole. Once an object passes the event horizon,
This
it is
discovery
thought to be
goes
lost
beyond
forever,
science.
dragged
It has deep
inexorably toward the
philosophical and
singularity at the center
existential
of the black hole.
implications.
However, recent developments in
discovery
theoretical
is
physics
just
have
the
called into
beginning of an
question
exciting
whether the
new
event
era in
horizon is
scientific
truly the
exploration.
impenetrable boundary we've
Look
always
at that
assumed
spike.
it to be.
It's off the charts.
One of the most
readings
famous
confirm it.
challenges to the
A
conventional view
gravitational
of the event
ripple,
horizon
just as we
came from the
hypothesized.
black hole information paradox. This paradox arose from the work of Stephen Hawking, who showed that black holes emit a form of radiation known as Hawking radiation
this discovery
due to
mean for
quantum
the search
effects
for
near the
life
event
on Earth?
horizon. This radiation allows black holes to slowly lose mass and eventually evaporate, leading to the question, what happens to the information contained within the black hole? According to the principles of quantum mechanics, information cannot be destroyed. But if matter falls into a black hole and the black hole eventually evaporates through Hawking radiation, what happens to the information contained within that matter? Does it disappear
Dark energy
forever, or
accelerates
is it
the
somehow
expansion of the
encoded in
universe,
radiation
causing
emitted by
voids
the
to
black
grow
hole?
larger, and
The
galaxies to
resolution of
become
this
increasingly
paradox is still
isolated.
an open
The
question,
anomaly
and
disappears
it
if
may
we
provide
factor in
new
the spin
insights
alignment.
into the true nature of black holes
The new framework
and their
is
event
stabilizing.
horizons.
This changes
Some
everything.
theories suggest that instead of being a
Cosmic
one-way barrier,
voids formed
the
as a
event
result of
horizon
the
might function
universe's
more like a
expansion
gateway,
after the Big
a
Bang.
portal through which information and
Some
energy could be transferred or even reconstructed. If the event horizon is not the ultimate trap we once thought it to be, it could lead to new
Could
theories
this
of
new anomaly
wormholes or
be tied
connections
to dark
between
matter,
different regions of
the invisible
space-time.
substance that
This would
makes up
fundamentally
most of the
alter our
universe's
understanding
mass?
of the role black holes play in the universe. Black holes as bridges. The possibility of wormholes. One of the most intriguing possibilities is that black holes could act as wormholes, hypothetical tunnels through space-time that could connect distant parts
Dark
of the
matter
universe.
plays a crucial
In
role
theory,
in the universe's
a wormhole
structure,
could allow for
helping to
faster
form
than light
galaxy
travel,
clusters
or
and
even
filaments
connect
that
different
surround
universes.
voids.
That
If black
signature
holes
right there.
are
It's the
indeed
rarest
connected
isotope
to
sequence
wormholes,
known. I've
they
never
may
seen
serve
it
as
in a nebula
bridges
before.
rather than mere
Unbelievable.
traps for
It
matter.
changes everything.
The energy
While this
readings
idea
are off
remains
the scale.
speculative,
It can't be
has been
stable.
explored in
Look at the
various
blue
models
shift.
of
It
quantum
is.
gravity and
We're
string
looking at a
theory.
transgalactic wormhole.
Some theories suggest that the gravitational forces near the event horizon could create a stable wormhole. providing a shortcut between distant regions of
There
space.
it is. The
The
gravitational
discovery
signature.
of the rarest phenomenon in the
Confirmed on all
universe could help to
channels. We
confirm or
found
refute
it.
these theories, shedding light on the true nature of black holes and their potential as cosmic portals. The future of black hole research. The study of black holes is entering an exciting new phase, with event horizon telescopes and gravitational wave observatories poised to provide
Look at this
unprecedented
section.
insights
It's completely
into these
empty.
enigmatic
A
objects.
void.
That's
The Event
impossible.
Horizon
The universe
Telescope,
isn't what we thought it
EHT,
was.
which captured the first ever image of a
that.
black hole's
The data
event
confirms
horizon in
it.
2019,
An Earth-like
is expected to
exoplanet in the
continue its
habitable zone.
groundbreaking
This
work,
changes
allowing
everything.
scientists to study black holes in greater
The
detail than ever
existence of
before.
cosmic voids
By
challenges
studying
our
the behavior of
understandings
light
space
and matter near the
time.
event horizon, we hope to gain a deeper understanding of how black holes function and perhaps unravel some of the biggest mysteries surrounding them. Moreover, the detection of gravitational waves from merging black holes has opened a new window into black hole physics. By studying the waves generated by black hole mergers, scientists can learn about the properties of black holes, including their mass, spin, and size.
The search
These
for this rare
observations are
phenomenon
providing
was
critical
not
data
easy.
that could help
It
resolve some of
required
the
years of
paradoxes surrounding
technological
black
innovation
holes
and
and lead to
breakthroughs.
new breakthroughs in our understanding of gravity, space-time, and quantum mechanics. Conclusion: a new era of understanding. Black holes have long been
This
considered the
discovery
most
could
mysterious and
rewrite our
extreme objects in
understanding of the
universe.
universe's
While our
evolution.
current understanding of black holes is rooted
This
in the theory
discovery
of general
doesn't just
relativity,
add to our
new
knowledge of the
discoveries and
universe.
theoretical
It
advancements
challenges it.
are forcing us to
It
question
represents a
what we
leap
know
in-
about these enigmatic phenomena. From the singularity
This
problem to the
discovery
role
forces
of
a
event
paradigm
horizons,
shift in our
black
understanding
holes
of the
challenge our
universe.
understanding of
It's not-
space, time, and the fundamental
This
forces of
discovery
nature.
goes beyond science.
As we continue
It has
to
deep
explore the nature
philosophical
of
and
black holes,
existential
we may
implications.
find that they are far stranger and more complex
This
than
discovery
we've ever
is
imagined.
just the beginning of
The
an
rarest
exciting new
discovery in
era
the
in
universe
scientific
could provide the
exploration.
key to understanding
Look at the
black
flux
holes
reading,
in
right
ways
near the
that we have
core.
yet to grasp. Are they really the
heavens, the
cosmic
data
traps
holds.
we think they are?
It's
Or are they
unmistakable.
something far more profound? Portals,
Voids don't
bridges, or
just sit
gateways
empty.
to new realms of
They also
space-time?
influence the movement of galaxies.
The discovery of black holes has opened up a
The
new
spike in
era
the
of
oxygen
cosmic
levels confirms
exploration.
it. We're
And as
looking
our
at a
understanding
habitable
of these
super
objects evolves, we may find that the true nature of black holes is still
With
more
new space
mysterious than we
telescopes
can
like
fathom.
JWST
The speed of
and
light
future
has
missions
been a
like the Square
cornerstone of modern
Kilometer
physics
Array,
for over a
the-
century. According to
This
Einstein's theory of
discovery
relativity,
changes
the
everything.
speed of light in a
The
vacuum
rarest
is the
phenomenon
ultimate
in
speed
the
limit of the
cosmos.
universe.
Advanced
Nothing
technologies
can travel
like
faster than
gravitational
light.
wave detectors
This
and radio
principle is
telescopes
embedded in many
have
of the most
transformed our
fundamental
ability
theories in
to explore
physics,
space.
including our understanding of space-time, energy, and even causality. Light, traveling at roughly 300,000 kilometers per second,
the energy
serves as
signature
a
here
reference point
contradicts
for
the
the structure of the
instability
universe
boundary. The model
itself.
doesn't hold. Wait,
For nearly as
we
long
adjust
as
the
the
spatial
theory of
parameters,
relativity has been established, the speed of
Cosmic
light has
voids
been
formed
considered
as a
an
result of the
immutable
universe's
constant,
expansion
with
after the
far-reaching
Big Bang.
implications for
Some
everything
regions
from the
became
flow
denser.
of time to the very structure of space. However, recent discoveries and theoretical proposals have begun to challenge this long-held belief.
Could this new
Could the
anomaly
speed
be
of
tied
light,
to dark
the ultimate
matter,
cosmic
the
limit,
invisible
be
substance
wrong?
that makes up
Could
most
faster
of the
than light
universe's
travel or
mass?
communication be possible?
Could this
And
rare
if it is,
discovery be
what would
tied
it
to
mean
dark
for our
matter or
understanding of
dark
physics,
energy?
space, and
Two
the
of the
future of
universe's
technology?
greatest mysteries.
In this chapter, we will explore the possibility that the speed of light might not be the universal speed limit we've always assumed. From breakthroughs in quantum mechanics to the exploration of theoretical concepts like tachyons, wormholes, and quantum entanglement, we will examine the evidence
energy
and
spike
ideas
right there,
that
it
challenge the
matches the
speed of
lensing
light.
signature.
What
We
if the
have
universe
confirmation.
doesn't operate under
This
the
changes
constraints we've
everything
assumed?
about star
And what would
formation.
that mean for
Dr.
everything we
Sharma,
know about physics?
Look at the energy readings.
The speed of
It can't
light
be.
in relativity.
That's a stable wormhole.
In Einstein's special theory of
gravitational disturbance
relativity,
detected
the
in the
speed of light
unexplored
is not
sector.
only a
It's
constant,
subtle,
but also a
incredibly
fundamental
powerful.
feature
It
of
shouldn't
space-time.
exist. Check
The theory
readings
states
again.
that the speed
Look
of
at the
light in a
kilonova
vacuum
signature.
is the same
It
for all
matches the
observers, no
gravitational
matter
wave
their
data.
relative motion.
We found it.
This was a
We
radical
actually found
departure
it.
from Newtonian mechanics.
What if these
which
vast
assumed
cosmic
that
voids are not
time
mere
and space
absences
were
of matter,
absolute,
but windows
and
into
that the
higher
speed of light
dimensions
was
and
relative to
parallel
the observer's
realities?
motion? One of the most famous results of special relativity is the time dilation effect. As an object approaches the speed of light,
These
time
redshift
slows
surveys,
down
they aren't
relative to an
uniform.
outside
Good
observer.
heavens, look at the
This
scale of
effect has
that
been
void.
experimentally
It
verified
challenges
in many
everything we
ways,
thought we knew.
including through
That's
the
the
use of
anomaly.
atomic clocks flown
stable.
on aircraft, where the clocks on the plane
is it.
run slower compared to those
Breakthrough
on
we
Earth.
needed for the Genesis
The
project.
closer an object gets to the speed of light, the slower time moves for that object, which has profound implications for our understanding of both space and time. Relativity also tells us that as an object moves closer to the speed of light, its energy requirements increase exponentially. This means that as an object
From our
approaches
home in
the
the
speed
Milky
of
Way,
light,
we
it would
zoom
require
out
an
past
infinite
the
amount of
local
energy to reach
revealing
that
the
speed,
massive scale
making it
of-
impossible for anything with mass to actually reach the speed of light. Thus, the speed of light has been accepted as an ultimate limit,
Wait,
beyond
look at the
which no
gravitational
object or
data,
signal
the
can
chirp.
travel. However,
It's
this
stable.
principle
We
of
did it.
relativity,
After
so
all this
central to
time.
modern physics, is based on observations in our current understanding of space-time. But what if new discoveries or new insights into the structure of space-time suggest that this limit is not absolute? What if we find a way to bypass this speed limit, allowing us to travel faster
This
than
discovery
light?
could rewrite our
Quantum
understanding
mechanics
of the
and
universe's
faster than light
evolution,
phenomena.
from cosmic
Quantum
inflation to
mechanics is the
galaxy
branch of
formation.
physics that deals with the behavior of particles on the smallest scales, atoms and
This
subatomic
discovery
particles.
doesn't just add to
While
our
quantum
knowledge of the
mechanics
universe.
works remarkably
Also,
well in describing the
This
strange and
discovery forces a
counterintuitive
paradigm
behavior of
shift in
particles,
our understanding
it
of the
also presents
universe.
challenges to our
It's not
traditional
just another
understanding
cosmic
of
event.
speed
This
and
discovery
time.
goes beyond science.
One of the most
It has
puzzling
deep
phenomena in
philosophical
quantum
and
mechanics
existential
is
implications.
quantum entanglement.
What does it mean for
In an
humanity's
entangled
place in the
system,
universe?
two particles become linked in such a way
This
that the
discovery
state
is
of one
just the
particle
beginning of an exciting
instantaneously
new
affects
era
the state
in
of the other,
scientific
no matter
exploration.
how far apart they are.
The data
This
is
phenomenon
undeniable.
occurs
A
faster than the speed
gravitational
of
anomaly
light,
of this
suggesting that
magnitude
some
changes
form of
everything.
instantaneous communication might be possible.
Voids don't just
even
sit
across
empty.
vast
They also influence
distances.
the movement of galaxies.
This phenomenon was
Galaxies
famously
within voids
described
move
by
more
Einstein
slowly.
as spooky action at a
This
distance.
anomaly
and
reshapes
it
the
directly
search for life,
challenges the idea that
revealing new
information
regions within
cannot
the
travel
Milky Way
faster
where
than the
habitable
speed of
planets.
light. Although quantum entanglement doesn't violate relativity in the traditional sense, it does not allow for faster-than-light communication of information. It raises questions about our
Advanced
understanding of the
technologies,
limitations
from
of
these
space and
radio
time.
telescopes
If
to
particles can be
gravitational wave
instantaneously linked over vast distances, what does this say about the nature of space-time itself? Could this instantaneous interaction between entangled particles
The current
be
model
a
doesn't
clue
account
that
for the energy signature
faster-than-light
here.
phenomena are possible? Furthermore, the
If we
field of
adjust
quantum
the
tunneling
parameter-
provides further evidence of particles behaving
After
in
the
ways
Big
that
Bang,
defy
the
classical
universe
physics.
expanded
In quantum
rapidly.
tunneling, particles can pass
Gravity
through
pu-
energy barriers that they would not be able to
Cosmic
surmount
voids
according to
vary in
classical
size,
physics,
from tens
suggesting
of
that there are
millions to hundreds of
shortcuts
millions of
through
light years
space
across.
that do not abide by
Could this
traditional
new anomaly
constraints.
be tied to
These
dark
phenomena
matter,
seem to
the
suggest
invisible
that there are
substance that
aspects of
makes
the
up
quantum
most of the
world that
universe
operate
mass?
outside the established boundaries
Could this
set by
rare
relativity.
discovery be tied to
Could
dark
these
matter
quantum effects
or
be
dark
leveraged
energy?
to achieve
Two
faster-than-light
of the
travel or
universe's greatest
communication?
mysteries.
Tachyons, theoretical particles
Dark
that
energy
travel
is a force causing the
faster than light.
accelerated
One of the
expansion
most
of the
famous
universe.
theoretical
And it
particles
plays a
that could
critical role.
potentially travel faster than light is the tachyon. Tachyons were first proposed in the 1960s as hypothetical particles
This is
that
it.
always move
The
faster
rarest
than
phenomenon recorded in
According
a century.
to the theory, tachyons would
We're
have
witnessing the
imaginary
birth
mass,
of a new
property that
galaxy.
makes them behave
The
very
energy
differently
readings are
from the familiar
stabilizing.
particles
Incredible.
we encounter in
The
everyday
gateway is
life.
real.
While we
Everything
cannot
has
detect
changed.
tachyons directly, they remain a subject
readings
of
are
theoretical
fluctuating
interest in
wildly.
It
physics.
shouldn't exist.
Tachyons would
If this is
violate the
accurate,
traditional
everything we know
energy-mass
about
relationship
galactic
in
physics
special
is wrong.
relativity.
Look at the
According
data.
to the theory,
chirp is resolving.
tachyons
We have
could never slow
confirmation,
down
it's a
to
merger.
the speed of light.
Unbelievable, we
They would
found
always
it.
exceed it. However, because their mass is imaginary, they could potentially possess properties that allow them to interact with the fabric of space-time in ways that are outside the scope of standard physics. If tachyons exist, they could offer a new way of thinking about faster-than-light travel. The idea of
vast regions,
tachyons
they're
has been
completely
explored
empty.
in various theoretical contexts,
The universe is
including
structured
string
with these
theory and
voids.
quantum field
It changes
theory,
everything.
where they are sometimes
There it is,
invoked as part of
the
a
Krios
mechanism to
phenomenon.
explain the structure of space-time
I can't believe
at
it.
very high
After all
energies.
this time, we
Although
actually
no
did it.
experimental evidence for
Sentences are
tachyons has
great.
been found,
The
their
existence
theoretical
of cosmic
existence
voids
continues to
challenges
spark
our
the
understanding of
imagination of
space and
physicists
time.
interested in breaking
They
the
refer-
light-speed barrier. Wormholes, shortcuts, through space-time. Another possibility for faster-than-light travel is the idea of wormholes, hypothetical passages through space-time that could connect distant parts of the universe. A wormhole is like a shortcut through space and time, allowing for instantaneous travel between 2 points. The concept of a wormhole
There it is,
comes from
the
Einstein's
gravitational
equations
signature.
of general relativity,
Unmistakable.
which
We
predict
have
the
detection.
existence of bridges in space-time that could, in theory, connect different regions of the universe. Wormholes are often depicted in science fiction as portals for faster-than-light travel.
The
While
universe
no
is
wormholes
organized
have
in a
been discovered,
vast,
the
interconnected
mathematical
structure
possibility of
called
their
the
existence has
cosmic
been
web.
confirmed. In fact, some scientists believe that black
This
holes
discovery
could be
could
the entrances
rewrite
to
our
wormholes,
understanding of the
potentially
universe's
connecting
evolution.
distant parts of space or even different universes through these
This
cosmic
discovery
tunnels.
doesn't just add to our
However,
knowledge of
even
the
if
universe,
wormholes do
it challenges
exist,
it.
traveling through them presents significant challenges. The exotic matter required to keep a wormhole stable is theoretical and has yet to be detected.
This
Some
discovery
theories
goes beyond
suggest
science.
that the energy
It has
required
deep
to create
philosophical
or
and
maintain a
existential
wormhole
implications.
would be enormous,
What does it mean for
potentially
humanity's
exceeding
place in
the
the
energy
universe?
content of an entire galaxy.
This discovery is
Nonetheless,
just the beginning
the idea
of an exciting
wormholes
new
opens
era
up
in
exciting
scientific
possibilities for
exploration.
faster-than-light travel,
The
and their
energy
study
readings
may
are
lead
off
to
the
new
charts at
insights
this
into
coordinate.
space-time and the structure of the
Incredible.
universe.
We've detected a
Faster-than-light
gravitational
travel,
anomaly.
the Alcubierre Drive. One of the
Voids
most
don't just
exciting
sit empty.
proposals for
They
faster-than-light
also
travel
influence the
is the
movement of
Alcubierre
galaxies.
Drive, a theoretical concept
does this
developed by
discovery
physicist
mean for the
Miguel
search for life
Alcubierre in
beyond Earth?
1994.
Explore the implications
The
of this
Alcubierre
anomaly for
Drive
finding
proposes a
habitable
method of
planets.
faster-than-light travel by manipulating space-time itself. Instead of moving an object faster than light through space, the idea is to contract space in front of the object and expand space behind it, creating a warp bubble that moves the object faster than the speed of light without violating the laws of physics. In theory, this warp bubble could allow for faster-than-light travel by compressing space in front of a spacecraft and expanding it behind, creating a localized region of space where the spacecraft would be stationary within the bubble, but the bubble itself could move faster than light. The key to this concept is that the spacecraft isn't technically moving faster than light. It is the
So
space
that's how
around it
relativity
that is being
connects to the
manipulated.
quantum field.
While the Alcubierre
It's
Drive
beautiful.
remains purely theoretical and would require vast amounts of energy, potentially more than the total mass energy of a star, it has captured the imagination of many scientists and science fiction enthusiasts. If the technology could ever be realized, it could revolutionize space travel, making journeys between distant stars a reality. However, current research suggests that the
infinite
energy
expanse,
requirements for such a
where
drive
light
are
years
far
are but a
beyond our
whisper.
current capabilities, and it may be centuries before we could harness this technology, if it is even possible. The future of faster-than-light travel. As our understanding of the universe continues to evolve, the possibility of faster-than-light travel remains one of the most tantalizing concepts in modern physics. From quantum entanglement to wormholes and the Alcubierre Drive, scientists continue to explore the
alignment
theoretical
holds true.
foundations of faster-than-light travel
Yes,
and the implications
just
it
as
might
the
have
tablets
for the future
foretold.
of space exploration. The discovery of new phenomena, such as the rarest thing in the universe, could provide new insights into space-time and gravity, potentially leading to breakthroughs in our ability to manipulate space and time. Whether or not faster-than-light travel becomes a reality in our lifetimes, the pursuit of this idea forces us to think beyond the conventional limits of physics and envision a future where the universe is no longer beyond our reach. Conclusion. Breaking the light speed barrier. The speed of light has long been viewed as the ultimate cosmic speed limit, but recent discoveries and theoretical models suggest that this fundamental principle may not be as absolute as we once believed. Quantum mechanics, tachyons, wormholes, and the Alcubierre Drive are just a few of the ideas that challenge the very notion of the speed of light as a universal constant. As we continue to explore the mysteries of the universe, we may find that faster-than-light travel is not only possible, but could one day become a reality. The future of space exploration is full of unknowns, and the discovery of new phenomena could provide the breakthroughs needed to push beyond the limits of conventional physics. The speed of light, once thought to be the ultimate barrier, may eventually be revealed as just one piece of a much larger, more complex cosmic puzzle. Gravity is perhaps the most familiar force in the universe. It is the force that holds us to the Earth, governs the motion of the planets, and shapes the structure
transition
of
is
galaxies.
complete.
It's what causes objects to fall,
Superposition
what keeps the
achieved.
moon in orbit
The energy
around Earth,
readings are
and
stable.
what gives weight to everything in the universe. In short, gravity is the force that binds the cosmos together. For centuries, gravity was a mystery. It wasn't until Isaac Newton formulated the law of universal gravitation in the 17th century that we began to understand how gravity worked on a large
As
scale.
we journey into the cosmic ocean,
Newton's law
we find
explained that
ourselves
every
adrift
object
in a
in the
sea of
universe exerts a
stars and
force of
shadows.
attraction on every other object. And the strength of this force depends on the masses of the objects and the distance between them. For centuries, Newton's laws described gravity with remarkable precision, and they became the foundation for classical mechanics. Then came Albert Einstein and his theory of general relativity, which revolutionized our understanding of gravity. Einstein proposed that gravity is not just a force exerted by masses, but a curvature of space-time itself. In Einstein's view, objects with mass cause space-time to bend around them, and this curvature is what causes other objects to move in curved paths. This idea was confirmed through many groundbreaking experiments, most notably by observing the bending of light around massive objects like the sun during a solar eclipse. While general relativity has been incredibly successful in explaining many phenomena, such as the orbits of planets, the behavior of black holes, and the bending of light, there is still much about gravity that we don't understand. In fact, gravity remains one of the most mysterious forces in the universe, with many questions yet to be answered. What if everything we think we know about gravity is wrong? What if the way gravity works is fundamentally different from how we've been taught? Could gravity, as we know it, be an illusion? And what would that mean for our understanding of space, time, and the very fabric of the cosmos? In this chapter, we will explore the mysteries of gravity, question the assumptions we've made about how it works, and examine new theories that challenge our current understanding of this fundamental force. The limits of general relativity. General relativity is one of the most successful theories in the history of science. It has passed every test thrown at it, from the bending of light around stars to the detection of gravitational waves. Yet, despite its success, there are still many unanswered questions about gravity, especially when it comes to extreme environments such as black holes and the very early universe. One of the biggest problems with general relativity is that it cannot be reconciled with quantum mechanics, the theory that governs the behavior of particles on the smallest scales. While general relativity works brilliantly on large scales, describing the motion of planets, the behavior of galaxies, and the warping of space-time, quantum mechanics describes the strange and unpredictable behavior of particles at the atomic and subatomic level. The two theories are incompatible in their current forms, and the search for a theory that unites both is one of the biggest challenges in modern physics. At the center of a black hole, for instance, the gravitational forces are so intense that space-time itself is warped beyond recognition. The predictions of general relativity break down in these extreme conditions, and we cannot use the theory to describe what happens inside a black hole's singularity, the point of infinite density at the center. General relativity also fails to explain what happens in the early universe, where conditions were so extreme that quantum effects should have played a major role in shaping space-time. In short, general relativity is an incomplete theory, and while it works in many situations, cannot explain the full range of gravitational phenomena. This raises the possibility that our understanding of gravity, based on general relativity, is fundamentally flawed. Perhaps gravity doesn't work the way we think it does, or maybe there's something we're missing about how it operates on the smallest and largest scales. The quantum nature of gravity, the search for a unified theory. At the heart of the quest to understand gravity is the search for a theory of quantum gravity, a theory that would unite the principles of general relativity with the rules of quantum mechanics. Quantum gravity would provide a complete framework for understanding how gravity behaves at both large and small scales. However, developing such a theory has proven to be an extraordinarily difficult task. The reason quantum gravity is so challenging that it involves trying to combine two very different descriptions of reality. General relativity describes gravity as a curvature of space-time, a smooth, continuous structure. Quantum mechanics, on the other hand, describes forces and particles as discrete, governed by probabilities and wave functions. These two views of reality are fundamentally incompatible in their current forms, which is why a unified theory remains elusive. There are several approaches to quantum gravity, including string theory and loop quantum gravity. String theory proposes that the fundamental particles in the universe are not point-like objects, but rather tiny, vibrating strings. These strings can exist in multiple dimensions beyond the familiar 3 dimensions of space and 1 of time. String theory has the potential to unify gravity with the other fundamental forces,
was a canvas
like
of endless
electromagnetism
darkness,
and the strong
waiting
and weak
for the
nuclear
colors
forces.
of creation to bloom.
However, string theory remains highly speculative, and much of it is still untested by experiment. Loop quantum gravity, on the other hand, attempts to quantize space-time itself, breaking it up into discrete chunks rather than treating it as a smooth continuum. This theory suggests that space-time has a granular structure with a finite number of quantum states, and gravity is a result of the interactions between these states. While loop quantum gravity has shown promise in certain areas, it still faces significant challenges, especially when it comes to making predictions that can be tested in the real world. Both of these theories are still in their infancy, and neither has been fully accepted by the scientific community. The search for a unified theory of gravity remains one of the biggest open problems in modern physics. But could this search ultimately reveal that gravity, as we understand it, is not what we think it is? Modified gravity. Theories challenging the standard model. While general relativity has been incredibly successful in explaining the behavior of gravity on large scales, there are alternative theories that suggest gravity might operate differently under certain conditions. One such theory is modified gravity, which proposes that gravity behaves in ways that deviate from Einstein's predictions, particularly on cosmological scales. One of the most well-known modified gravity theories is MOND, modified Newtonian dynamics, which was proposed by physicist Milgram in the 1980s. MOND attempts to explain the rotation curves of galaxies, how the speed of stars and galaxies doesn't slow down as expected based on Newtonian mechanics. Instead of invoking dark matter, MOND suggests that gravity behaves differently at very low accelerations, such as those found in the outskirts of galaxies. Another modified gravity theory is AFR gravity, which proposes modifications to the equations of general relativity in order to explain the accelerated expansion of the universe. Instead of relying on dark energy,
Cosmic voids
FR
vary
gravity
in size,
modifies the way
from
gravity
tens of
operates
millions
on
to hundreds of
cosmological
millions of
scales,
light years across.
potentially offering an alternative explanation
Could
for
this
the
new
observed
anomaly
acceleration.
be tied to dark matter?
Theoretical
The invisible
models of
substance
modified
that
gravity
makes up most
challenge
of
the
the
traditional
universe's
view
mass?
that gravity works according to
Could
the
this
smooth
rare
curvature
discovery
of
be tied
space-time
to dark
described
matter
by general
or
relativity.
dark energy? Two of
These
the universe's
modified gravity
greatest
theories are
mysteries.
gaining attention because they offer alternative explanations for phenomena that are typically attributed to dark matter or dark energy. If gravity
Dark matter
behaves
plays a
differently
crucial
than we think,
role in the
then
universe's
perhaps dark
structure,
matter is not
helping
the
to form
elusive
galaxy
substance we've been
clusters
searching
and
for.
filaments that
And
surround
dark energy
voids.
might not be an unknown force causing the accelerated expansion of the universe. The holographic principle. Gravity as an emergent phenomenon.
Deep
One of the
within the
most
galactic
radical
core,
ideas about
scientists
gravity
have
is the
witnessed the
holographic
impossible.
principle, which
A
suggests
stable-
that
The
gravity,
gravitational
along with
distortion is
space
off
and
the
time
charts.
itself,
Cross-reference
might
the
be an
radio
emergent
data. It's a
phenomenon
perfect
rather than a
match.
fundamental
We
force.
did it. We actually did
According
it.
to this principle, the universe we
voids,
experience,
long thought
three-dimensional
empty,
space and
may in
time,
fact
could be a projection
be
from a
bounded
two-dimensional surface, much like a hologram. The holographic principle has its roots in black hole thermodynamics, particularly the work of Jacob Bekenstein and Stephen Hawking,
Look at this.
who discovered
There's
that
nothing
black
here.
holes have entropy and temperature.
void.
This led to the realization that the information contained within a black hole could be encoded on
energy
its
readings
surface,
are
known as the
unprecedented.
event horizon.
Look at the
In
gravitational
other
lensing.
words,
It
the
confirms
three-dimensional
propulsion
space
theory.
inside the black
rate.
hole could be
The
described by
existence of these
information
voids
on its
challenges our
two-dimensional
understanding of
surface.
space and time.
In recent
They
years, the
symbolize not just
holographic principle
emptiness.
has gained traction as a potential way to unify
The Milky
gravity
Way,
with quantum
with
mechanics.
its hundreds of billions of
Some
stars,
theorists
is a vast
suggest
and
that
rich
space-time
galaxy.
and gravity could emerge from the interactions of quantum fields on a two-dimensional surface rather than being fundamental properties of the universe. If this idea holds true, gravity would no longer be an intrinsic force, but an emergent property of a deeper, more fundamental reality. Gravity and the future. A new paradigm? As our understanding of gravity continues to evolve, we may find that it operates in ways we never imagined. The discovery of the rarest phenomenon in the universe may provide the breakthrough we need to understand gravity in a completely new light. Whether gravity is an emergent phenomenon, a modification of Einstein's theory, or something entirely
This
different,
discovery could
the next
rewrite
steps
our
in gravitational
understanding of the
research
universe's
will reshape
evolution.
our understanding of the universe. The search for a unified theory of quantum gravity may reveal that gravity is not the smooth, predictable force we once thought. Instead, it may be part of a larger, more complex framework that includes quantum mechanics, space-time fluctuations,
In the press.
and the very fabric of
This
the universe
discovery goes
itself.
beyond science.
By
It has
continuing
deep
to probe the
philosophical and
mysteries of
existential
gravity and
implications.
space-time, we may uncover a new model
This
of the
discovery
cosmos,
is just the
one that will
beginning of an
challenge
exciting
everything we
new
thought
era
we knew
in
about
scientific
the forces
exploration.
that shape our universe.
Look at that
Conclusion.
spike. It's off the
Rethinking
charts.
gravity.
The readings
Gravity
confirm
is
it.
one of the most
A
familiar
gravitational
forces in the
ripple,
universe,
just as we
yet it remains
hypothesized.
one of the most mysterious. While general relativity has been incredibly successful in explaining how gravity works on large scales, it is clear that our understanding of gravity is far from complete. Whether through the search for quantum gravity, the exploration of modified gravity theories, or the discovery of new phenomena, we are on the cusp of a new understanding of this fundamental force. Gravity may not be what we think it is. It could be an emergent property of space-time, a modification of Einstein's theory, or something entirely new. As we continue to explore the mysteries of the universe, we will undoubtedly uncover more about the true nature of gravity.
Dark
And in
energy
doing so,
accelerates
we may
the
discover
expansion
that
of
the
the
universe is even
causing
stranger
voids to
and
grow
more
larger,
complex than
and
we ever
galaxies
imagined.
to become increasingly
Space-time,
isolated.
the
The
very
anomaly
fabric that forms
disappears
the
if we
structure of
factor
the
in the spin
universe,
alignment.
has long been a cornerstone
The
of
new
our
framework is
understanding of the
stabilizing.
cosmos.
This changes
According
everything.
to Einstein's theory of general
Cosmic
relativity,
voids form
space and
as a
time
result
are
of the
intricately
universe's
connected into a
expansion after the
four-dimensional
Big
fabric,
Bang.
which is warped and
Some
curved by the mass and energy of objects. This warped space-time is what causes the phenomenon we know as gravity. It explains
Could
everything
this new
from the
anomaly
falling
be
apple
tied to
the
dark
orbits
matter,
of planets
the
around
invisible
the sun.
substance that makes up most of the
Space-time has
universe's
shaped our
mass?
understanding of the universe on a cosmic scale. For over a century, this concept has been one of the
Could this
foundational
rare
pillars of
doppelganger
modern physics. Yet, despite its remarkable success in explaining the large-scale structure of the universe, there are still many questions and inconsistencies
Dark
regarding
matter
the
plays a
nature of
crucial role
space-time.
in the universe's structure,
Can space-time,
helping to
as
form
we
galaxy
understand it,
clusters
truly
and
be
filaments
the
that
complete
surround
description
voids.
of the
That
universe's
signature
structure?
right there. It's the
Could there be
rarest
more to the
isotope
story?
sequence known.
Perhaps
I've never
hidden
seen it in a
dimensions
nebula
or
before.
layers of reality that lie beyond the space-time we observe.
Energy readings are off
In this
scale.
chapter,
It
we'll
can't be
challenge the
stable.
conventional
Look at the blue
wisdom
shift.
about
It is.
space-time.
We're looking at
While
a transgalactic
space-time has
wormhole.
proven to be a powerful framework for understanding gravity and the behavior of massive objects, we will explore new theories and ideas that suggest space-time might not be the whole story.
signature.
From the possibility of higher
Confirmed on all
dimensions to
channels.
the concept of space-time as an illusion, we will delve into the frontiers of theoretical physics to understand what might lie beyond the familiar space-time fabric. The foundations of space-time, Einstein's legacy. In 1915, Albert Einstein fundamentally altered our understanding of
this section.
space and
It's
time
completely
with his
empty.
general
A
theory of
void.
relativity.
That's impossible.
This
The universe
revolutionary
isn't what
theory
we thought
described
it was.
gravity not as a force transmitted
Look at
through
that.
space,
The data
but as a
confirms
warping
it.
of the very
An
fabric of
Earth-like
space and time
exoplanet in the
itself.
habitable zone.
In
This
Einstein's
changes
view,
everything.
objects with mass, like stars, planets, and
The
black
existence
holes,
of cosmic
create
voids
curves in the
challenges our
space-time fabric,
understandings of
and it is
space and
these
time.
curves that dictate how objects move through space. General relativity was confirmed by a series of landmark experiments, such as the bending of light around the sun during a solar eclipse and the observed motion of Mercury's orbit, which could not be explained by Newton's laws of gravity. For the most part, General relativity
In the
has been
cosmic
incredibly
extremes
successful
of
in
a black
explaining the
hole,
large-scale
reveals
structure
its
of the
rarest
universe,
phenomena.
from the behavior of planets,
The search
the
for this
dynamics
rare
of
phenomenon
galaxies,
was not
the
easy.
expansion of the
It
cosmos.
required years of technological
Einstein's
innovation
concept
and
of
breakthroughs.
space-time, however, relies on the idea that space and time are connected, forming a smooth, continuous fabric. In this model, space-time is static and behaves
This
predictably
discovery
based
could
on the
rewrite
distribution
our
of
understanding
mass
of
and
the
energy.
universe's evolution.
But while general relativity has been widely
This
accepted as one of
discovery
the
doesn't
cornerstones
just
of modern
add to our
physics,
knowledge of the
there are
universe.
growing signs
It
that the
challenges
concept
it.
of space-time
It
as a
represents a
continuous,
leap
smooth
in-
fabric might be far more complicated than we realize.
This discovery forces a
The
paradigm
quantum
shift in
nature
our
of
understanding of the
space-time.
universe.
One of
It's
the
not-
most significant challenges to our understanding
This
of space-time
discovery goes
comes
beyond
from
science.
quantum mechanics,
It has deep
the branch
philosophical
of
and
physics that
existential
describes the
implications.
behavior of particles at the smallest scale.
This discovery is just
Quantum
the beginning
mechanics
of
has
an exciting
revolutionized
new
our
era
understanding
in
of the
scientific
subatomic
exploration.
world, introducing
at the
concepts
flux
like
reading, right near the
wave-particle
core.
duality, uncertainty principles,
Good heavens,
and
the
quantum
data
entanglement.
holds. It's
At these tiny
unmistakable.
scales, space-time behaves in ways that are
Voids
completely
don't just
different
sit
from what we
empty.
observe on a large
They
scale.
also influence the
While
movement
general
of galaxies.
relativity describes space-time as a smooth continuum,
spike in the
quantum
oxygen levels
mechanics
confirms
suggests
it.
that
We're
space-time
looking
might
at a
be
habitable
fundamentally
super-Earth.
discrete at very small scales, something akin to the granularity of a
With
digital
new space
image.
telescopes like
At the Planck scale,
JWST
the
and
smallest
future
possible
missions
scale
like
in
the Square
physics,
Kilometer Array,
space-time may
the
not be smooth and continuous,
This
but
discovery
instead could be
changes
pixelated,
everything.
consisting of quantized
rarest
units that are too
phenomenon
small
in the
to be observed
cosmos.
directly.
Advanced technologies
This idea
like
is at the heart of the
gravitational
search for
wave detectors
quantum
and radio
gravity, a
telescopes
theory that
have
seeks to
transformed our
unify general
ability to
relativity
explore
with quantum
space.
mechanics. The goal is to describe gravity and space-time as a quantum phenomenon, just like the other fundamental forces described by quantum mechanics.
Look, the energy signature
This
here
would
contradicts the
fundamentally change our
M-stability boundary. The
understanding of
model doesn't
space-time
hold.
and
Wait,
open up
if
new
we adjust the
possibilities
spatial
for exploring
parameters,
the
fact-
nature of reality.
Cosmic
Higher
voids
dimensions,
formed as a result of the
beyond the
universe's
familiar,
expansion after the Big
space-time.
Bang. Some
One of the
regions
most
became
fascinating
denser.
possibilities in modern physics is the existence of higher dimensions, dimensions beyond the familiar three of space, length, width, height, and one
Could
of
this
time.
new anomaly be tied
The
to
idea
dark
that
matter,
the universe could
the
have
invisible
more than
substance
4
that makes up
dimensions is
most
not
of the
new.
universe's mass?
In fact, it's been part of
Could
theoretical
this rare
physics for
discovery
over
be
a
tied to
century,
dark
but
matter
recent
or dark
developments in
energy,
string theory and
two of the
related
universe's
fields have
greatest
brought it to the
mysteries?
forefront of scientific inquiry. In string theory, the most promising candidate for a unified theory of quantum gravity, the universe is thought to have extra spatial dimensions that are curled up so tightly that they're nearly impossible to detect. According to string
The energy
theory,
spike
the
right there,
fundamental
it
building
matches the
blocks of the
lensing
universe
signature.
are not
We have
point-like
confirmation.
particles, but
This
tiny
changes
vibrating
everything
strings.
about star formation.
These strings
Dr.
can
Sharma,
vibrate in
look at
multiple
the energy
ways,
readings.
with each vibration corresponding
It
to a
can't
different
be.
particle
That's a
or
stable
force.
wormhole.
The theory suggests that there are 6
gravitational
additional
disturbance
dimensions
detected in the
beyond the
unexplored
familiar
sector.
4.
It's
But
subtle,
these
but
extra
incredibly
dimensions are
powerful.
so
It shouldn't
small
exist.
and compacted
Check the readings again.
that they cannot be
Look at the
observed
kilonova
at our
signature.
scale.
It matches
If
the
higher
gravitational
dimensions
wave data.
exist, it would completely
found it.
alter our
We actually
understanding of
found it.
space-time. These
What if
additional
these vast
dimensions
cosmic
could
voids
explain
are not mere
phenomena
absences
that
of
general
matter,
relativity
but
and
windows
quantum
into higher
mechanics
dimensions and parallel
cannot,
realities?
such as the nature of gravity and the behavior of particles at extremely high
detected in the
energies.
Milky
The
Way
existence
raises
of higher
intriguing
dimensions
questions.
might also provide the key to solving some of the
redshift
biggest
surveys,
mysteries
they
in
aren't
physics,
uniform.
such
Good
as
heavens,
dark
look at the
matter,
scale of
dark
that
energy,
void.
and the
It challenges
unification of
everything we
forces.
thought we knew.
That's
Space-time
the
as an
anomaly.
emergent phenomenon.
It's stable.
A radical idea in modern
This is
physics
it.
is that space-time
The breakthrough
itself
we
may not
needed
be
for
a
the
fundamental
Genesis
property
project.
of the universe, but rather an emergent phenomenon. This idea, proposed by theorists like Juan Maldacena and Eric Verlinde, suggests that space-time could emerge from deeper layers of reality, much like how temperature emerges from the movement of particles. In this view, space-time
From our
might not
home
be
in
an
the Milky
intrinsic
Way,
part of the
we
universe,
zoom out
but
past
rather
the
a
local
manifestation
group,
of more
revealing the
fundamental
massive
laws or
scale of
principles. According to this idea, gravity could be an emergent force, something that arises from the interactions of quantum particles.
Wait,
or
look at the gravitational
fields.
data. The chirp.
Instead of being a fundamental force
It's
that
stable.
exists
We
independently,
did it! After
gravity
all
might
this
be a
time.
result of the way space-time itself behaves on the smallest scales. In this framework, space-time is not a continuous entity, but a projection of a more fundamental set of principles, and gravity is a secondary effect that emerges from these deeper principles. This idea has the potential to revolutionize our understanding of space-time, suggesting that the smooth fabric we
cosmic
observe
inflation
might
to
not be
galaxy
the full
formation.
picture. Instead, it could be a shadow of something much more complex.
This
If
discovery
space-time is
doesn't just
indeed an
add to
emergent
our knowledge
property,
of the
then the
universe.
true nature of the
So,
universe could lie
this
in
discovery
understanding the
forces a
fundamental
paradigm
principles
shift in our
that give
understanding
rise
of
to
the
this fabric,
universe.
which might
It's
involve
not just
quantum
another
mechanics,
cosmic event.
string
This
theory,
discovery
or
goes beyond
completely new
science.
ideas
It
we
has
have
deep
yet to discover.
philosophical and existential
The
implications.
holographic principle.
What does it mean for
Space-time
humanity's
as a
place in the
projection. One of the most mind-bending ideas
This
in
discovery
theoretical
is
physics
just the beginning
is the
of an
holographic
exciting
principle,
new era in
which proposes
scientific
that the
exploration.
three-dimensional universe we experience might actually
The
be a
data is
projection
undeniable.
of a
A
two-dimensional
gravitational
surface.
anomaly of this magnitude
This concept
changes
is inspired
everything.
by black hole thermodynamics,
Voids
specifically
don't just
the work
sit
of
empty.
Jacob
They also
Bekenstein
influence the
and
movement
Stephen
of
Hawking,
galaxies.
who found that
Galaxies
black holes
within
have
voids
entropy
move more
and temperature,
slowly.
and their information could be
This
encoded on
anomaly
the surface
reshapes
of
the
the
search
event
for
horizon.
life, revealing
The
new regions
holographic
within the
principle
Milky Way
suggests
where
that the
habitable planets.
information contained within a region of space can be described by the data on its boundary, rather than within the region itself. This idea implies that our perception of space-time and the vast universe we see could be an illusion, a projection of a more fundamental reality that exists in fewer dimensions. If true, this theory would profoundly challenge our notions of space,
The current model
time,
doesn't
and
account for the
reality
energy
itself.
signature here.
According to the holographic principle, all the information about
adjust
the
the
universe could be encoded on a two-dimensional surface
After
of the
the Big
cosmic
Bang,
horizon,
the universe
outer boundary of
expanded
the observable
rapidly.
universe. This would
Gravity
mean that everything we experience, from the
Cosmic
stars to the
voids vary in
galaxies,
size,
could be
from tens
projections
of
from a
millions to
deeper
hundreds of
underlying
millions of light
reality.
years across.
While the holographic
Could this new
principle is still
anomaly
highly
be tied to
speculative
dark matter,
and largely
the invisible
theoretical,
substance that
it has
makes
gained
up most of
traction
the
in recent
universe
years,
mass?
especially in the study
Could
of
this
black
rare
holes and
discovery
quantum
be
gravity.
tied to dark matter
Is
or
space-time
dark
an
energy?
illusion?
Two of the
As we
universe's
examine the
greatest
nature of
mysteries.
space-time from these different perspectives, one of the
Dark
most
energy
profound
is a
questions
force
that
causing the
arises
accelerated
is whether
expansion of the
space-time is an
universe,
illusion.
and it plays a critical role.
Could the very fabric of the universe, the dimensions we inhabit, and even the flow of time itself be constructs that arise from something more
This is it.
fundamental?
The rarest
Could
phenomenon
our perception
recorded
of
in a
space and
century.
time be a limited
We're
view of a
witnessing
much
the birth
larger,
of a new
more
galaxy.
complex reality
The
that we
energy
cannot
ratings are
directly observe?
stabilizing. Incredible.
If space-time
The
is
gateway is
indeed an
real.
illusion or an
Everything
emergent
has
phenomenon,
changed.
this would mean that our entire
readings are
understanding of the
fluctuating
universe,
wildly. It
our
shouldn't
notions
exist.
of distance,
If this is
duration,
accurate,
and motion,
everything we know about
would need
galactic
to be
physics is wrong.
rethought.
Look at the
This
data.
would have
The chirp is
far-reaching
resolving.
implications
Yeah,
for
confirmation, it's a
cosmology,
merger.
gravity,
Unbelievable.
quantum
We found
mechanics,
it.
and even our understanding of the nature of reality itself. It would suggest that our experience of space and time is simply a projection of a deeper hidden truth, one that we are only beginning to grasp. Conclusion: the future of space-time. Space-time has been
These
one of the most
vast regions
successful
are
and
completely
enduring
empty.
concepts in modern physics.
The
It
universe
has allowed
is
us to
structured with
understand
these
gravity,
voids.
the
It
structure of
changes
the universe,
everything.
and the
There it
behavior
is,
of celestial
the
bodies
Krios
with
phenomenon.
remarkable precision.
I can't
But as we
believe
venture
it.
deeper
After
into
all
the
this
mysteries
time,
of the cosmos,
we actually did it.
we begin to realize
These are
that
for you.
space-time, as we
The
currently
existence of
understand
cosmic
it,
voids
may not
challenges
be the
our
whole
understanding
story.
of space and time.
The search for a more complete
They-
theory of space-time, one that can reconcile general relativity with quantum mechanics, promises to uncover deeper truths about the nature of reality. Whether through the discovery of higher dimensions, the development of quantum gravity, or the exploration of the holographic principle, the future of space-time research is full of exciting possibilities. The rarest phenomenon recently discovered
There it
could be
is,
the
the
key to
gravitational
unlocking these
signature.
deeper layers of space-time,
Unmistakable. We have
offering new
detection.
insights into the true structure of the universe. As we continue to explore these mysteries, we may find that the fabric of the cosmos is far stranger, more complex, and more beautiful
The
than we
universe
ever
is
imagined.
organized in a
The
vast,
true nature of
interconnected
space-time
structure
may be far
called
beyond our
the
current
cosmic
understanding,
web.
and the journey to uncover it is just beginning.
This discovery
One of the most
could
exciting
rewrite
and
our
mind-boggling
understanding of the
ideas to
universe's
emerge from
evolution.
modern physics is the multiverse theory. This
discovery
theory
doesn't
suggests
just
that our
add to
universe,
knowledge
with
of
its
the
vast
universe.
galaxies,
It challenges
stars, and
it.
planets, is just one of potentially infinite universes that make up a much larger multiverse. While this might sound like something straight out of science fiction,
This discovery
the idea
goes
of
beyond
the multiverse
science.
has
It has
gained
deep
traction in
philosophical
recent
and
years
existential
as
implications.
scientists grapple
What does it
with
mean
some
for
of the most
humanity's
profound
place in the
questions
universe?
in cosmology, quantum
This
mechanics
discovery
and
is
the
just
nature
the
of
beginning
reality
of an
itself.
exciting new era
The
in
multiverse
scientific
theory
exploration.
challenges everything we thought
The
we
energy
knew about
readings
the
are
universe.
off the charts at this
If there are
coordinate.
indeed infinite universes, then
Incredible.
everything we know,
We've detected
our
a
laws of
gravitational
physics, our
anomaly.
understanding of space-time, and even our very
Voids don't
existence
just sit empty.
could be just
They
one
also
possible
influence the
outcome in
movement
an
of
infinite
galaxies.
array of possibilities.
What does this
This notion
discovery mean for the
upends our
search for
concept
life
of
beyond
the
Earth?
unique universe
Explore
in
the
which we
implications
live,
of this anomaly
suggesting
for
that
finding
reality
habitable
may be
planets.
far stranger and more diverse than we can even begin to imagine. In this chapter, we will explore the multiverse theory, its origins, and the various ways it could potentially explain the mysteries of the universe. We will examine how it challenges our understanding of reality and what it means for the future of scientific exploration. Could there be infinite versions of ourselves in different universes, each living out different lives? Could the multiverse theory hold the key to understanding some of the greatest unanswered questions in science? The origins of the multiverse theory. The idea that our universe might be just one of many
So
has
that's
roots
how
in both
relativity
cosmology
connects
and
to the quantum
mechanics.
field.
It was initially a
beautiful.
philosophical notion, but has gained increasing support through scientific advancements and theories that attempt to explain the nature of the universe. 1. Cosmic inflation, the birth of the multiverse. The concept of the multiverse is closely tied to the theory of cosmic inflation. Proposed by physicist Alan Guth in the 1980s, cosmic
the
inflation
infinite expanse,
suggests that the universe
where
underwent
light
an
years are but a
incredibly
whisper.
rapid expansion in the first fractions of a second after the Big Bang. This expansion stretched space-time so quickly that the universe as we know it emerged from a quantum fluctuation in an almost instantaneously expanding bubble of space. While inflation explains many of the observed features of the universe, such as its large-scale homogeneity and the distribution of galaxies,
The alignment
it also
holds true.
suggests the possibility that inflation
Yes,
didn't stop
just
with
as
the
the
creation
tablets
of our
foretold.
universe. Instead, it could continue indefinitely, creating multiple bubble universes, each with its own laws of physics, constants, and properties. This is the essence of the eternal inflation model, which proposes that our universe is just one of an infinite number of universes, created through an endless process of inflationary expansion. According to this theory, new universes are constantly budding off from an inflating space-time, with each one having different physical parameters. These universes could vary widely in their characteristics. Some might be similar to ours, with similar physical laws and constants, while others could be vastly different, perhaps with different numbers of dimensions, different forces, or completely alien forms of life. Eternal inflation provides a framework for understanding how a multiverse could arise from the very fabric of space-time itself. It suggests that what we perceive as our universe is just a tiny pocket in a much larger, infinitely diverse multiverse. 2. String theory. Multiple dimensions and parallel universes. Another important theoretical framework that supports the multiverse theory is string theory. String theory, which aims to unify all of the fundamental forces of nature, including gravity, posits that the basic building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings can vibrate at different frequencies, and the way they vibrate determines the types of particles and forces they manifest. One of the most fascinating aspects of string theory is that it requires the existence of additional spatial
Superposition
dimensions beyond the familiar
energy readings
3
are
of space
stable.
and 1 of time. In fact, string theory suggests that there could be up to 10 or 11 dimensions in total, with the extra dimensions being compacted so small that they are undetectable by current experiments. This idea of extra dimensions opens the door to the possibility of a multiverse.
As we journey into
Some
the
versions
cosmic
of
ocean,
string theory
we
propose
find
that the
ourselves
extra
adrift in
dimensions
a
could be
sea of
branched
stars
into
and
separate
shadows.
universes, each with different properties based on how the strings vibrate and how the extra dimensions are compacted. These parallel universes would be completely separate from ours, with their own physical laws and constants, leading to a vast array of potential universes within the multiverse. The existence of parallel universes in string theory offers an intriguing solution to the fine-tuning problem, which asks why the constants of nature in our universe are perfectly suited for the existence of life. In a multiverse scenario, the fine-tuning might simply be a result of the vast number of possible universes, each with different physical parameters. In this framework, we just happen to live in a universe that supports life, but there could be countless others where life, as we know it, cannot exist. Types of multiverses. The multiverse theory is not a single unified idea. In fact, there are several different versions of the multiverse, each based on different theoretical frameworks and models. Let's examine some of the major types of multiverses that have been proposed. 1. The Level 1 multiverse, infinite universes with different regions. The Level 1 multiverse arises from the idea that space is infinite. If space extends infinitely in all directions, then at some point, the conditions that exist in our observable universe must repeat. This is based on the infinite monkey theorem, which suggests that in an infinite space, anything that can happen will happen. And therefore, regions of space that are exactly like our own must exist somewhere. In this model, our universe is just one part of an infinite, ever-expanding cosmos. There could be other regions of space that are indistinguishable from ours, with the same laws of physics and constants, leading to duplicate universes that have formed through the same process of cosmic inflation. While these universes would be indistinguishable from ours, they could still be vastly separated in space, making them unreachable and unobservable from our own universe. 2. The Level 2 multiverse, universes with different physical laws. The Level 2 multiverse arises from the theory of eternal inflation, as discussed earlier. According to this model, the universe is made up of multiple bubble universes that are continuously forming. Each bubble universe could have different physical properties, constants, and laws of physics. For example, one universe might have a different gravitational constant, a different number of spatial dimensions, or even different types of fundamental particles. This type of multiverse challenges our notion of universality in physics, suggesting that the laws of nature we take for granted might not be the same everywhere. The diversity of physical laws could mean that life as we know it would only be possible in certain universes, while other universes might be inhospitable to life. 3. The Level 3 multiverse, many worlds in quantum mechanics. The Level 3 multiverse is based on the many worlds interpretation of quantum mechanics. According to this interpretation, every time a quantum measurement occurs, the universe splits into multiple branches, each corresponding to a different outcome of the measurement. This means that every possible outcome of every quantum event actually happens, but in separate parallel universes. In the Level 3 multiverse, there could be countless versions of ourselves, each existing in a different parallel universe where different decisions were made or different events took place. This version of the multiverse is more philosophical in nature, as it suggests that every possibility that could occur in our universe, no matter how small or unlikely, actually does occur in a different branch of the universe. 4. The Level 4 multiverse, universes with different mathematical structures. The Level 4 multiverse takes the concept of the multiverse to its extreme, suggesting that there could be universes with entirely different mathematical structures. In this view, the laws of physics are not universal, but are simply the result of mathematical structures that could vary in different parts of the multiverse. These universes could have completely different kinds of matter, energy, and even different dimensions of space and time. This level of multiverse would encompass all possible mathematical structures, each giving rise to a distinct universe with its own physical properties and laws. The Level 4 multiverse is the most speculative and abstract form of the multiverse, as it challenges the very nature of reality itself, suggesting that there could be universes governed by completely different rules from the ones we experience. The philosophical implications of the multiverse. The idea of the multiverse has far-reaching philosophical implications. If the multiverse theory is true,
the
it would
universe was a
suggest that our
canvas of
universe is
endless
not
darkness,
unique, but just one
waiting
of
for
many.
the colors of creation
This could raise
to bloom.
profound questions about the nature of existence and the role of consciousness. If there are infinite universes, then does that mean everything that could happen has already happened, somewhere in some universe? The idea that there could be infinite versions of ourselves in different universes raises existential questions as well. Are we special in any way, or are we simply a random outcome of an infinite number of possibilities? The multiverse could imply that everything is not unique and that the events and decisions we make may not be as important as we once thought, because they are just one of many possibilities. Moreover, the multiverse challenges our perception of reality itself. If the laws of physics and the constants of nature are not the same everywhere, then what does that mean for our understanding of the fundamental nature of the universe? Are our laws of physics merely a random choice among many, or do they have some deeper significance? The answers to these questions could change the way we think about the cosmos and our place within it. Conclusion. What if everything we know about the universe is just one of many? The multiverse theory presents a profound shift in how we understand the universe. It challenges our assumptions about uniqueness, reality, and even the laws of physics. If the multiverse is real, then everything we know about our universe might be just one of many possible outcomes in a vast, infinite cosmos. As we continue to explore the implications of the multiverse, we may find that the universe is far more complex and diverse than we ever
Advanced
imagined.
technologies like
The discovery
gravitational
of new
wave
phenomena
detectors
and
and
the
radio
development of new
telescopes
theories
are
could
transforming our
ultimately
ability
reveal
to
that our
explore
universe
space.
is just one piece of a much larger, much more intricate puzzle. The possibility of infinite universes invites us to rethink
M
our
sigma
place in the
relation doesn't hold
cosmos
here. Look at
and
the data. It
challenges us
requires
to
a
consider
localized
the
field
true
fluctuation.
nature of
If we adjust for the
existence.
dark matter halo, the new
As
framework is
scientists
stable.
continue to probe the mysteries of the universe,
Cosmic
the concept
voids
of the
formed as a
multiverse
result of the
will
universe's
undoubtedly
expansion
remain
after the
one of the
Big
most
Bang.
exciting and
Some regions
controversial
of
ideas in modern physics.
Cosmic voids vary in size.
Whether or not we ever
from
find
tens of
direct
millions
evidence
to
for the
hundreds of
multiverse,
millions of light
the
years
idea
across.
itself invites us to dream
Could
beyond
this
the
new
boundaries of our
anomaly be
own
tied
universe,
to dark matter,
and to contemplate
the
a
invisible
reality that
substance
is
that
far
makes up
stranger,
most of the
more
universe's
complex,
mass?
and more awe-inspiring
Could this
than we
rare
ever
discovery
imagined.
be tied to dark
Space
matter
exploration
or dark
has
energy?
always been one of
Two of the
humanity's most
universe's
ambitious
greatest
and
mysteries.
awe-inspiring endeavors. For centuries, we've gazed at the stars, wondering what lies beyond our home planet. And over the last few decades,
Dark matter
our
plays a
ability to
crucial
reach
role
farther
in
into
the
space
universe's
has
structure,
advanced rapidly,
helping to form
bringing us
galaxy
closer
clusters
to
of
answering some of the
filaments
most
that surround
fundamental
voids.
questions about the universe. From landing on the moon to exploring the outer reaches of the solar system, humanity has made significant strides in its quest for knowledge about the cosmos.
Deep
But
within
as
the
much as we've
galactic core,
accomplished, we're
scientists
still
have
only
witnessed
scratching
the
the surface
impossible.
of what space
A
holds.
stable,
The gravitational
The vast
distortion is
expanse
off the
of the
charts.
universe is
Cross-reference the
full
radio
of
data.
mysteries.
It's a
Some
perfect
we have yet
match.
to discover,
We did it.
and
We
others
actually
that
did it.
challenge everything we think we know.
Cosmic voids.
The
long
future
thought empty,
of space
may in
exploration
fact
promises to be
bound
even more
for
revolutionary,
parallel.
with new technologies, missions, and theories pushing the boundaries of what we thought was possible. In this chapter, we'll explore the exciting new frontiers in space
nothing
exploration and what the future
A
holds.
void.
From missions to
Massive.
distant planets and moons to the possibility of human colonization
Energy
on
readings
Mars,
are unprecedented.
we'll examine the technologies and
gravitational
ideas that
lensing.
could shape
It
the next
confirms the
era of
propulsion
exploration.
This
Great.
We'll also look
The
at the ways
existence
in
of
which
these
new
voids
discoveries,
challenges our
like the
understanding of
recent
space
discovery
and
of the
time.
rarest phenomenon
They
in the
symbolize
universe,
not just emptiness.
could lead to breakthroughs that change everything we know
the
about
Milky
the
Way,
cosmos.
with its hundreds of billions
next
of stars,
giant leap.
is a vast and vast galaxy.
Human exploration of Mars. One of the most exciting frontiers of space exploration in the coming decades is the human exploration of Mars. For years, Mars has been considered the most likely candidate for humanity's first interplanetary colony. The red planet has a similar day length to Earth, water in the form of ice, and a relatively mild climate compared to the other planets in the solar
The
system.
search for this rare
These
phenomenon
features make it a
was
prime
not
target
easy.
for future
It
exploration
required
and
years of
colonization.
technological
NASA's Artemis program, which aims to return humans to the moon by the mid-2020s, is considered a crucial first step in preparing for missions to Mars.
This
The
discovery
experience gained
could
from landing
rewrite our
astronauts on the
understanding
moon
of the
and
universe's
establishing a
evolution.
sustainable presence there will be invaluable when it comes to reaching Mars. The technologies developed for lunar exploration, including life support systems, habitat construction, and long-duration space travel, will be directly applicable to Mars missions. NASA's long-term
In the
goal
press.
is to send humans to
This
Mars
discovery
in the
goes
2030s.
beyond science.
The
It has
plan
deep
involves sending
philosophical and
astronauts on a
existential
round-trip mission
implications.
that would last anywhere from 18 to 24
discovery
months,
is
with
just
the
the
crew
beginning
spending
of an
several months
exciting
on
new
Mars
era
conducting
in scientific
research
exploration.
and exploring the planet's surface.
Look at that spike. It's
These
off the
missions will
charts.
be incredibly
The readings
challenging,
confirm
as
it.
astronauts
A
will need to
gravitational
survive in an
ripple,
environment
just
with
as we
minimal
hypothesized.
resources and harsh conditions. The main obstacles include radiation exposure, the lack of a breathable atmosphere, and the extreme cold. To overcome these challenges, NASA and private space companies like SpaceX are working on developing new spacecraft, life support systems, and technologies for sustainable habitats. SpaceX's Starship, which is designed for deep space missions, including Mars, could become the vehicle that takes humanity to the Red Planet. With reusable rockets and a large cargo capacity, Starship has the potential to drastically reduce the cost of sending humans and supplies to Mars, making human colonization more feasible.
Dark energy accelerates
The human
the expansion
exploration
of the
of
universe,
Mars is
causing
not
voids
just
to
about
grow
scientific
larger,
discovery.
and galaxies to
It
become
also
increasingly
holds the
isolated.
potential for
The
humanity's
anomaly
future
disappears
as a
if we factor in the
multiplanetary
spin alignment.
species. By establishing a
framework
permanent
is
presence on
stabilizing.
Mars,
This
we can
changes
create
everything.
a backup for humanity in case of
Cosmic
catastrophic
voids
events on
form
Earth,
as a result
such as
of the universe's
natural disasters,
expansion after the
pandemics,
Big
or
Bang.
even climate change.
Some
Mars could become the first step in humanity's expansion beyond Earth, paving the way for further exploration of the solar system and beyond.
Could this
The
new
search for
anomaly be
life
tied to
beyond
dark
Earth,
matter, the invisible
exoplanets, and
substance that
habitability?
makes up most of the
One of the
universe's
most
mass?
profound questions in science is whether we are alone in the universe. For centuries, scientists have speculated about the possibility of extraterrestrial life, but only recently have we begun to have the tools to answer this question. The discovery of exoplanets,
Dark
planets
matter
that
plays a
exist
crucial
outside our
role
solar
in the
system,
universe's
has
structure,
revolutionized
helping
our
to form
search for
galaxy
life
clusters
beyond
and
Earth.
filaments that surround
Since
voids.
the discovery of
That
the first
signature right
exoplanets
there.
in the 1990s,
It's the rarest isotope sequence
astronomers
known.
have
I've
discovered
never seen it in a
thousands
nebula
of these
before.
distant worlds, many of which reside in the
Energy
habitable
readings
zone,
are off
the
the
region
scale.
around a star
can't
where
be
liquid
stable.
water could
Look
exist.
at the blue shift.
It is.
This has led
We're
to the
looking at a
exciting
transgalactic
possibility
wormhole.
that there may be Earth-like planets in other star systems with the right conditions to support life. The search for these planets and the study
There
of
it
their
is,
atmospheres
the
and
gravitational
compositions
signature.
is one of the most exciting areas of modern astronomy. Telescopes like the Kepler Space Telescope and the James Webb Space Telescope, JWST, have already provided valuable data on exoplanets and their potential for habitability. JWST, which is set to launch in 2021, will be capable of analyzing the atmospheres of
Look at this
exoplanets
section.
in
It's
unprecedented
completely empty.
detail,
A
searching
void.
for signs
That's
of water,
impossible.
methane,
The universe isn't
carbon
what we thought it
dioxide,
was.
and other gases that could indicate the presence
The
of
data
life.
confirms it.
An
The next
Earth-like
frontier in the
exoplanet
search
in the
for
habitable
extraterrestrial
zone.
life
This
is
changes
direct
everything.
detection. The ability to observe biosignatures,
The existence
or
of
chemical
cosmic
signatures
voids
of
challenges
life
our
in the
understanding
atmospheres of
of
distant
space and time.
exoplanets. This could be a game changer in the search for alien life, allowing scientists to determine whether life exists on planets outside our solar system. The discovery of even the most basic forms of life on another planet would have profound implications for our understanding of life in the universe. Space tourism, opening the door to space for all. While human exploration of other planets is a long-term
search for
goal,
this rare
space
phenomenon
tourism is
was not
already
easy.
becoming a reality.
It required years
Private
of
companies
technological
like
innovation
Blue Origin,
and breakthroughs.
Virgin Galactic, and SpaceX are working to develop commercial space travel for private citizens. These companies are making space more accessible than ever before, offering
This
suborbital
discovery
flights
could
that allow
rewrite
people
our
to experience
understanding of the
weightlessness
universe's
and see
evolution.
Earth from space. Virgin Galactic's
discovery
Spaceship
doesn't
2
just
is
add
already
to
in
our
the
knowledge
test
of the
flight stage,
universe.
with plans to begin
challenges it.
commercial flights for
It
tourists in
represents
the
a
near
leap
future.
in-
Blue Origin's New Shepard rocket is also designed to take
This discovery
passengers on
forces a
suborbital
paradigm
flights,
shift in our
offering a
understanding
brief
of the
but
universe.
thrilling experience
It's
of
not-
space travel. While these flights are
This
currently short
discovery
and
goes
expensive,
beyond science.
costing tens of
It has
thousands
deep
of dollars,
philosophical and
prices are
existential
expected to
implications.
decrease as the technology matures and becomes
This
more widely
discovery
available.
is just the beginning
In
of
the
an
long
exciting
term,
new
space
era
tourism
in
could
scientific
evolve into space
exploration.
travel for a wider
Look at
range
the
of
flux
people.
reading, right near the
Companies
core.
like SpaceX, with their ambitious
Good
goals for
heavens, the
Mars and
data
beyond,
holds.
are working on
It's
developing
unmistakable.
reusable spacecraft that could transport not just
Voids don't
astronauts,
just sit
but
empty.
ordinary citizens
They
into
also
space.
influence the movement
The development of
galaxies.
these technologies could eventually lead to space hotels,
spike in the
lunar
oxygen levels
resorts, and
confirms
even
it.
missions to
We're
Mars
looking at
for
a
private
habitable
individuals.
super-Earth.
Space tourism, though still in its infancy, is set to become a major
new space
industry in the coming
telescopes like
decades,
JWST
opening up the frontier
and
of
future
space to
missions like
more
the
people
Square
than ever
Kilometer
before.
Array. The
Space mining,
This
extracting
discovery
resources from the
changes
cosmos.
everything.
As
The
human
rarest
exploration of space
phenomenon in the
advances,
cosmos.
one of the most
Advanced
exciting
technologies
possibilities
like
is space
gravitational
mining,
wave
the
detectors
extraction
and
of
radio
valuable
telescopes
resources
have
from
transformed our
asteroids,
ability
the
to
moon,
explore
or even
space.
Mars. Many asteroids are thought to contain precious metals like platinum, gold, and iridium, as well as other resources that could be used for
the energy
manufacturing,
signature here
construction,
contradicts the
and even
M-stability boundary.
fuel
The model
production.
doesn't hold.
Space mining
we
could
adjust
become a
the spatial
game changer for
parameters,
Earth's economy, providing an abundance
Cosmic
of
voids
resources that
formed
could
as
be
a
used
result
to
of the
sustain
universe's
human life on
expansion
Earth
after the
or
Big
on other
Bang.
planets.
Some regions became
It could also
denser.
help alleviate resource shortages on Earth, such as the depletion of rare metals used in electronics and solar panels. Companies like Planetary
Could
Resources
this new
and Deep
anomaly
Space
be tied
Industries
to dark matter,
are already exploring the
invisible
potential
substance
for
that makes up
asteroid mining,
most of the
with
universe's
plans to
mass?
send missions to mine asteroids
Could
in the
this
next
rare
few
discovery
decades.
be tied to dark
While
matter
space
or
mining
dark
presents
energy?
many challenges,
Two of the
including
universe's
the development of
greatest
technology
mysteries.
to extract resources from space and the need for international regulation, it could offer a new way to support space exploration and human colonization. By obtaining resources directly from space, we could build sustainable habitats on the Moon, Mars, or other celestial
The
bodies,
energy spike right
reducing
there,
our
it
reliance
matches the
on
lensing
Earth-based
signature.
resources
We have
and making
confirmation.
space exploration
This changes
more feasible
everything
in the
about
long
star
term.
formation.
Dr.
The
Sharma,
role of
look at the
artificial
energy
intelligence in space exploration.
It can't be.
As
That's a
space
stable
exploration
wormhole.
becomes more complex and ambitious,
A
the
gravitational
role of
disturbance
artificial
detected in the
intelligence,
unexplored sector.
AI,
It's
is
subtle, but
becoming
incredibly
increasingly
powerful.
important.
It shouldn't exist.
AI
Check
is
the
already
readings
being
again.
used in many
Look at the
aspects
kilonova
of space
signature.
exploration,
It matches
from
the
autonomous
gravitational
spacecraft
wave data.
navigation to data
We found
analysis
it.
from
We
telescopes
actually
and
found
space missions.
What
In
if
the
these
future,
vast cosmic
AI could
voids
play
are
an
not mere
even
absences
bigger
of
role
matter,
in the
but
exploration
windows
of
into
distant
higher
planets,
dimensions and
moons,
parallel
and asteroids,
realities?
allowing for autonomous missions to areas that would be difficult or impossible for humans to reach.
Raises intriguing questions.
AI could also help with the development of
These
habitats
redshift
on other
surveys,
planets,
they aren't
assisting in
uniform.
everything
Good
from
heavens,
building
look at the
infrastructure
scale of that
to
void.
maintaining life
It
support
challenges
systems.
everything we thought we knew.
In the long
That's the
term,
anomaly.
AI could help
It's
humans
stable.
on Mars or the Moon to survive and
it.
thrive in harsh
The breakthrough we
environments,
needed for the
monitoring
Genesis
systems,
project.
performing repairs, and even making critical decisions in real time. Furthermore, AI could play a key role in the search for extraterrestrial intelligence, SETI. AI algorithms can process massive amounts of data much faster than humans, enabling the detection of potential signals
From our
from
home in
alien
the Milky Way,
civilizations.
we zoom out
With the
past
advancement of
local
AI,
group,
we may
revealing
be
the
able to
massive
process the
scale of
vast amounts of data collected from space and search for signs of life beyond Earth more efficiently than ever before. Conclusion:
Wait, look at the
the
gravitational
future
data.
of
It's true.
space exploration.
It's
The future
stable.
of space
We did it!
exploration is
After all
incredibly
this
exciting,
time.
with new technologies, missions, and possibilities opening up every year. From the human exploration of Mars to the search for life on distant exoplanets, the next phase of space exploration promises to expand our understanding of the universe in ways that were once
This
unimaginable.
discovery could rewrite our
Whether it's through
understanding
space
of the
tourism,
universe's
asteroid
evolution.
mining, or the
From
development
cosmic
of
inflation to
AI-driven
galaxy
missions,
formation.
humanity is poised to take the next giant leap into the cosmos. As we
This
continue to
discovery
explore the
doesn't
mysteries
just
of the
add to
universe,
our knowledge of the
we will
universe.
undoubtedly uncover
sir.
new phenomena,
This discovery
encounter
forces a
challenges,
paradigm
and make
shift in our
discoveries that
understanding of
change
the
everything we
universe.
know about space
It's not
and
just
time.
another cosmic event.
The future
Discovery
of
goes
space
beyond
exploration
science.
is boundless.
It has deep
and the
philosophical
journey
and
to understand the
existential
universe
implications.
has only
What
just
does it mean
begun.
for humanity's place in the
With
universe?
every discovery, we come one step
This
closer to
discovery
understanding
is
our
just
place
the
in the
beginning of
cosmos
an exciting
and
new
unlocking
era
the
in
infinite
scientific
potential of
exploration.
space. As we near the end of this
The
exploration
data is
into the vast
undeniable. A
unknowns of space,
gravitational anomaly
we are
of
left
this
with one
magnitude changes
profound
everything.
realization. The universe is far
Voids
more
don't
mysterious,
just sit empty.
complex,
They also
and
influence the movement
awe-inspiring
of galaxies.
than we could have ever
Galaxies
imagined.
within voids move more
The
slowly.
questions we've
Louis.
raised throughout this journey,
This
the
anomaly
nature of
reshapes
dark
the
matter,
search for life,
the enigma
revealing
of
new
dark energy,
regions within
the
the Milky
possibility
Way
of
where
faster than
habitable
light
planets.
travel, and the potential existence of infinite universes represent just a fraction of the mysteries that await us. The more we discover, the more we realize how much
Advanced
we don't know.
technologies, from these
And that
radio
is the beauty of
telescopes to
scientific
gravitational
discovery.
wave detectors.
For centuries, humanity has sought to understand its place in the cosmos. From the first time we gazed at the stars, we have asked, where do we come from? How did
The
the
current
universe
model doesn't
begin?
account for the
Are
energy
we alone?
signature here.
While we have
Yeah.
made incredible strides in our exploration
If
of the
we
universe,
adjust the burger-
these fundamental questions continue to drive us
After
forward.
the Big Bang,
Each
the
new discovery,
universe
whether
expanded
it's the detection
rapidly.
of a distant exoplanet
Gravity
or the confirmation of gravitational waves,
Cosmic voids
brings us
vary in
closer to
size,
understanding
from
the
tens of
vastness of
millions
space
to
and our
hundreds of
place
millions
within
of
it.
light years across.
Yet, despite
Could
our
this new
progress,
anomaly be
we are
tied to
still
dark
at the
matter,
very beginning
the
of this
invisible
journey.
substance that makes
The
up most
discoveries
of the
we've made
universe
so
mass?
far have changed the course of
Could
human
this
history.
rare discovery be
But they
tied
also
to
serve
dark
as a
matter
reminder
or dark
of
energy?
how much more is
Two
out
of the
there,
universe's
waiting
greatest
to be
mysteries.
uncovered. The universe is full of surprises,
energy
some of
is a
which
force
challenge
causing the
everything we think we
accelerated
know about the
expansion of the
laws of
universe,
physics,
and it plays
space,
a
and
critical
time.
role.
It's this uncertainty, the unknown, that makes space exploration so exciting and endlessly fascinating.
This is it.
In
The
this final
rarest phenomenon
chapter, we
recorded in a
reflect on the
century.
incredible journey we've taken
We're
and
witnessing
look to
the
the
birth
future.
of a new galaxy.
We'll discuss the implications
The
of our
energy readings
findings,
are
the
stabilizing.
mysteries that
Incredible.
remain, and the
The
role
gateway
of
is
curiosity in pushing the
Everything has
boundaries of
changed.
knowledge. We will also emphasize the importance
readings are
of embracing the
fluctuating
unknown.
wildly.
It
For
shouldn't
it is this
exist.
pursuit of the
If this
unknown
is accurate,
that will continue
everything we
to
know
propel
about galactic
humanity
physics
toward
is
new
wrong.
frontiers.
Look at the data. The chirp is
The
resolving.
endless
We have
quest for
confirmation.
knowledge.
It's a merger.
Unbelievable.
From the
We
moment
found
humans
it.
first looked up at the night sky, we have sought answers to the most profound questions about existence. Ancient civilizations created myths and legends to explain the stars and the planets. Philosophers and scientists, from Aristotle to Galileo to Einstein, have pondered the nature of the universe.
These vast
Each
regions,
step
they're
in this
completely
intellectual
empty.
journey has led to new
The
insights and
universe
discoveries.
is structured with these voids.
Today,
It
we are
changes
in the
everything.
midst
There
of
it
an
is.
extraordinary
The
era
Krios
of
phenomenon.
space exploration. The advent
can't
of
believe
space
it.
telescopes
After
like
all this
Hubble and
time,
James Webb,
we actually
the
did it.
launch of interplanetary
Tendencies are
missions like
predictable.
Mars rovers and
The
Voyager,
existence of cosmic
and the
voids
rise of
challenges
private
our
space companies
understanding of
like
space and
SpaceX
time.
are all pushing the
They-
boundaries of what we know. Yet, for all our achievements, the universe remains an unfathomably vast and mysterious place. With each new discovery, we find that our understanding of space and time is incomplete. And that is what drives us forward, the desire to know more, to explore further, and to push the limits of human knowledge. While we have uncovered much about the universe,
There it is,
its
the
age, its
gravitational
composition,
signature.
and its structure, we
Unmistakable.
still don't
We
have
detection.
answers to the biggest questions. What is dark matter? And why does it make up most of the universe's mass? What is dark energy? And why is it causing the accelerated expansion of the universe? Are we truly
universe
alone in
is
the
organized
cosmos,
in a
or is
vast,
there life out there
interconnected
waiting to be
structure
discovered?
called
The answers to
cosmic
these
web.
questions may not come easily, but the pursuit of these answers is what makes
This
space
discovery could
exploration
rewrite
so
our
exciting.
understanding of the
The universe
universe's
is a great
evolution.
mystery, and it is this mystery that continues to inspire generations
discovery
of
doesn't just add to our
scientists,
knowledge of the
dreamers,
universe.
and
It
explorers.
challenges it.
The role of curiosity in pushing boundaries. Curiosity is the driving force behind scientific exploration. It is the spark
This
that ignites
discovery
the
goes
desire
beyond
to
science.
ask questions,
It has deep
challenge
philosophical and
assumptions,
existential
and seek the
implications.
truth.
What does it mean for
Without
humanity's
curiosity,
place in the
we
universe?
would not have developed the tools to explore
This
the farthest
discovery
reaches
is
of
just
space,
the beginning
nor
of an
would we have
exciting
made the
new era
groundbreaking
in
discoveries that
scientific
have reshaped
exploration.
our understanding of the universe.
The energy readings are
At its
off
core,
the charts at this
space
coordinate.
exploration is about answering the fundamental
Incredible.
questions of existence.
We've detected a
Why does the
gravitational
universe
anomaly.
exist in the way it does? How did it come to
Voids
be?
don't just sit
And
empty.
most importantly,
They also
are we
influence
alone
the
in
movement
this
of
vast,
galaxies.
infinite expanse?
What does this
These
discovery
questions
mean
have
for the
haunted
search for
humanity for
life beyond
centuries,
Earth?
and the quest to
Explore
answer
the
them has
implications
led
of
to
this
some of the
anomaly
most
for finding
remarkable
habitable
achievements
planets.
in the history of science. From landing on the moon to observing the farthest galaxies with the Hubble Space Telescope, each step has been motivated by an insatiable curiosity to understand the cosmos. The role of curiosity in science is not just about finding answers. It's also about expanding our imagination and challenging our preconceived notions about the world around us. Curiosity leads us to ask bold, new questions and to explore ideas that might once have seemed impossible. In the same way that Einstein's theory of relativity revolutionized our understanding of space and time, new ideas and discoveries in space exploration
So
are
that's
poised
how
to
relativity
transform our
connects to the
understanding of the
quantum
universe.
field.
Every
It's
new
beautiful.
breakthrough challenges us to think bigger, to imagine a universe more strange and complex than we ever thought possible. The next great leap: expanding humanity's reach. As we look to the future, The possibilities for space exploration are boundless. The discoveries we have made so far are just the beginning. With new technologies, new theories, and new missions on the horizon, the next great leap in space exploration is already beginning. Whether it's through the human exploration of Mars, the search for habitable exoplanets, or the quest to understand the most mysterious forces of the cosmos, the future holds endless potential for new discoveries. One of the most exciting prospects is the human colonization of Mars. Over the next few decades, we may see humans set foot on the red planet, establish permanent colonies, and begin to explore its resources. The technological advancements required for such missions, from life support systems to propulsion technologies, will undoubtedly lead to breakthroughs that could benefit humanity on Earth as well. The colonization of Mars is not just about exploring a new planet, it is about ensuring the long-term survival of the human race and creating a multi-planetary species. The discovery of exoplanets, planets orbiting other stars, has already begun to revolutionize our understanding of the potential for life beyond Earth. With future missions like the James Webb Space Telescope, we will be able to study the atmospheres of exoplanets in unprecedented detail, searching for signs of habitability and perhaps even life. These discoveries could be some of the most profound in human history, reshaping our understanding of our place in the cosmos. Moreover, advancements in space travel technology, such as the development of warp drives or quantum propulsion, could drastically reduce travel times to distant stars, opening up new frontiers for exploration. These technologies could one day allow us to venture beyond our solar system and visit distant exoplanets, perhaps even establishing colonies on planets in other star systems. While we are far from this reality, the seeds of these technologies are already being planted, and the future of space exploration holds vast potential. The implications of the unknown. The unknown is what makes space so captivating. We don't yet know what lies at the edges of the observable universe, or what mysteries await us on distant planets and moons. But it is precisely because of this unknown that space exploration holds such profound significance for humanity. Each new discovery about the universe forces us to rethink our place in the cosmos and our understanding of reality itself. Whether it's the discovery of dark matter, the detection of gravitational waves, or the search for extraterrestrial life,
as we journey
each
into the
breakthrough
cosmic
challenges
ocean,
us to think
we
beyond
find
the limits
ourselves
of our
adrift
current
in a
knowledge
sea of
and to
stars and
embrace the
shadows.
vast unknown. Space exploration is more than just a scientific endeavor. It is a journey of self-discovery. As we explore the universe, we gain new insights into the nature of life, time, and space. We learn not only about the cosmos, but also about ourselves. Our pursuit of knowledge is a reflection of our innate curiosity, our desire to understand the world around us, and our unyielding drive to explore the unknown. Conclusion: the infinite journey ahead. The future of space exploration is limitless. As we continue to push the boundaries of what's possible, we will uncover new mysteries, make groundbreaking discoveries, and expand humanity's reach beyond the confines of Earth. The discovery of the rarest phenomenon in the universe has shown us how much we still have to learn and how much more the cosmos has to offer. The universe is a vast, awe-inspiring place, and our journey to understand it is only beginning. Whether we're exploring distant planets, uncovering the secrets of dark matter and dark energy, or searching for life beyond Earth, the quest for knowledge will continue to drive us forward. The unknown awaits, and with it comes the promise of new discoveries that will change everything we know about the universe. As we embrace the unknown, we remember that space exploration is not just about finding answers. It's about asking the right questions and embracing the limitless possibilities that lie ahead. The journey of discovery is never truly complete. It's a journey that will continue for generations to come, inspiring us to reach for the stars, to seek out the unknown, and to unravel the mysteries of the cosmos.